these are all operators. I am not putting that caret on top of it. These are all operators. Okay. Now, as I mentioned earlier, you can diagonalize Lz, one of the generator, one of this angular momentum operators, and you can from there one of the generators, and the other two will not be diagonal. It is not be diagonal matrix, but L square, okay, will be diagonal, because it commutes with all of them. It commutes with all of them. So, this is basically the idea. Now, if I take L, so let me write x, y, z. Okay. Let me write x, y, z, the position operators, and then I can ask the question, what is Lz with x, with Lx? I can construct that. It is y p z x, this is p y here. Have I written it correctly? No, sorry, this is not correct. This is x p y minus y p x, y p x. Okay. That is what we will have, r cross p will have. Now, I ask the question, what is Lz with x? Okay. Lz with x will be, you can work out the commutator, right? You know how to work out these commutators, all of you? It is very simple. If you have commutator of, this is what you have to use, just for your benefit. If I want AB with C, commutator of matrix is AB with C, what you have to do is, this will be equal to A with B comma C plus A comma C with B. That is a matrix formula, nothing to do with physics or anything, simply matrix multiplication. Because AB, this is using the fact that AB, this thing itself is AB C minus C AB. This is what that equation is. So, if you expand this, you will find it to be this. You write this, then it will be ABC minus ACB. Similarly, ACB minus CAB. That is what the two terms which are there. You will find exactly what I have written on the left hand side. So, using that, you can work out all these commutators. Okay. You will expect, so this is what is there, and I will tell you what will happen. This is what is called rotations, because x, y, z, Lz is a kind of an operator which leaves the z part invariant, does not touch it, but xy plane it rotates. So, this is x axis, this is y axis, and this is z axis perpendicular. This whole plane is rotated, okay, whereas L is the z part of it is untouched. That is what is axis of rotation is z. That is the meaning of that object, and we know what is going to happen, and I will tell you what is going to happen. When you rotate it, when you rotate this, it will go to x prime, y prime, z prime. And as I told you, it is an axis about z axis. So, z prime will not change, z prime will not change. So, if I write this as a matrix multiplying x, y, z, since z will not change, this has to be 1. This is 0, this is 0, 0, 0. Z has not changed. So, it is only xy plane which is rotated. Okay. Now, you know what will happen there also, it is very simple. It is cos theta here, sin theta here, minus sin theta here, cos theta here. That is what that object is going to be. Okay. That is what that object is going to be. Now, I can, this is as simple as that, it is as simple as that. Now, I can write this matrix, okay, in this form. I will write it for you. I will write it as e to the power I theta and then a matrix which is Liz. I will call it Liz. Okay. Now, what is that matrix? So, if this thing is there, you can expand it. E power I, you can expand it. The first term will be 1, okay, first term will be 1, and that first term is simply multiplying identity matrix multiplying x, y, z. What is the second term? What is the second term in that expansion of e power I theta z? You know e power x. You know e power x or not? What is it? 1 plus x square by factorial 2 plus x cube by factorial 3, etc. As simple as that. I am not. So, the first term is, this is 1 here plus I theta times Liz. I will put a dot dot dots. For small values of theta, I can keep only to the leading order. If theta is very small, if theta is 0, nothing happens. If theta is 0, you expand by, there is no rotation, you go back. If theta is very small, this is x axis, this is y axis, I rotate this whole thing by a small amount, 1 degree or half a degree or 1 minute or 1 second, whatever you want to have, very, very small amount. You do not have to worry about what you are writing for the higher terms. So, that is what I am put this rest of the terms as dot dot dots, okay, because I want to know what is Liz. So, this is a transformation, Liz is a transformation which gives you for very small values of theta. Now, I should know what is the small values of theta. When theta is very close to 0, cos theta is 1. So, that matrix is 1. This is 1, let me write 1. And what about sin theta? It is theta, you should keep up to first order, right? You should keep up to 0. Sin theta is 0 is correct when theta is 0. But I am not saying theta is 0. Theta is equal to 0 is identity. I am not making any transformation. But I want to make small transformation, right? Infinitesimal transformation. So, I should keep theta but to the order theta. I should drop theta square and theta cube, etc. So, what is it? It is equal to theta. This is theta, this is 0, and this is minus theta, this is 1, 0, 0, 0, 1. That is what the first term is going to be. The first term is going to be that, right? Now, I should then, what if this is equal to this whole thing, if this whole thing, okay, that is what that matrix is. So, what is Liz? What is Liz? You already have theta. So, you can say, it is equal to this whole thing. You can subtract 1. You subtract 1 from this, then you will get I theta Liz. I theta Liz is this matrix minus 1, right, minus identity matrix. So, I theta Liz is 0, 0, 0, because the 1 will cancel out. Then you will have I theta here, it will be theta minus theta, I am kind of thing, and then, so this is that matrix. So, I can even write this theta outside and this theta outside and call it theta here, right. I can cancel this theta also on both sides. So, ILZ is what is that matrix, okay. ILZ is that matrix. So, what is it I can do? If I know LZ, if I know this LZ which is for that I should multiply by minus I. If I multiply by minus I, it is minus I 0 1 1 minus 1 0. Okay. You can even put that I inside. You can even put minus I here, and this minus I and minus 1 will become I here. So, LZ is that matrix. LZ is that matrix which has done a small rotation, right. It has become a small rotation. Now, if you know that matrix, I can substitute it here. Once you know this matrix, I can substitute it here, which means e to the power I theta LZ, where LZ is this matrix. You have found out what is LZ. So, you simply write the exponential of that matrix. Whatever formula is there for e power x. E power x is, I said, 1 plus x squared by factorial 2, x cube by factorial 3, etc., is true even for matrices. E power a, as where a is a matrix, is 1 plus a square by factorial 2, where a is a matrix, a cube by factorial 3, etc. If you do that, you will exactly get this matrix. You will exactly get. So, you should, first term is going to be this, which we have, that is what we have used. The second term from there will turn out to be square of this matrix, and the square of the matrix is exactly what you have for the other terms, right. When you keep up to the leading order, second order, up to second order, cos theta is, it starts with 1 plus theta square by 2. Sin theta is theta, the next term is theta cube, do not bother about it, right, only up to theta square. Similarly here, and this one will be 1 plus theta square by 2. So, that is what you will get from this matrix. So, to all orders you will get the same thing. So, that is what is the first thing. So, I told you what is LZ. Similarly, I can work out what is LX. I can work out what is LX, I can work out what is LY by considering the same kind of matrices which I wrote. I wrote, if it is say, I wrote cos theta, sin theta, 0, minus sin theta, cos theta, 0, 0, 0, 1. This is the LZ part which I wrote. The matrix which I wrote, not LZ, the rotation up to angle theta along keeping z axis as an axis of transformation. Now, if it is x axis, I keep rotation about x axis. So, what is that matrix? I want to keep x axis invariant, that means my axis is x, I rotate this room in this way, right. This is y axis, this is z. So, in this plane I rotate. So, what will be that matrix? So, the same cos theta, sin theta, minus sin theta will appear in different places. It will be in the yz plane, right. It will be in the yz plane, in which case this will become 1, this will become 0, this will become 0, this will become 1 sin theta, and this will become minus sin theta, and this will become cos theta. This is the rotation about x axis, similarly for y axis. So, each one you can work out Lx, Ly, Lz. So, now you have 3 matrices Lx, Ly, Lz. You already have 3 matrices Lx, Ly, Z coming from xpy minus ypx. So, you wrote down a commutation relation. You wrote down a commutation relation based on this one Lx with Ly is I h bar Lz. So, I am dropping that h bar for this is the commutation relation. I can write for Ly Lz and then Lx Lz also, all the 3 of them. There are 3 commutation relations I can write and they obey that. Now, I have given a matrix form for that, because what is that matrix which I wrote for you? It is this matrix. If I have this matrix 0 I minus I or minus I here plus I here, if I keep this as Lz, similarly I work out Lx, similarly I work out Ly and find that commutation relations of these matrices. Matrix multiplication is all of you are familiar. You can multiply 2 matrices AB minus BA. You will find exactly identical. Okay? So, that is why we call this Lx, Ly, Lz. If I want to do small transformation, use Lx times theta or Ly times theta or Lz times another theta, 3 angles. You can rotate by small angle about z axis, y axis and x axis. So, if you do that, that matrix will give you the answer for it. It is 1 plus that theta times I theta times Lz. That matrix will give you. If you want to find large rotation, big rotation, not theta is not small, 30 degrees, 25 degrees, 50 degrees. If you want to do such rotations, what you should do is find what is for small transformation and exponentiate it, e to the power I theta Lz. You build the full transformation using small transformations. You make the 30 degrees transformation by a small amount. Okay, that is what it is. It is like you build the high speed by small speeds, right, from 0 to something. That is what you are doing. So, that is why these objects like Lx, Ly, Lz or L, which I have written down, they are all generators. They are all called generators of rotation. They are all called generators of rotations. Okay? Is the meaning clear? Okay, that is what you know the small one, you can build the big one. You generate the big one by exponentiating the small ones. That is all you are doing. And that is what this thing is. And you have this object which obeys the commutation relations here, and I have given an explicit representation or explicit matrix form which is for all the 3 matrices. But you can ask the question, are these the only matrices which can be there? Because you know, if I work out for this matrix, say Lz, for this matrix Lx, Ly, Lz, for this I can work out what are the eigenvalues of Lz. The eigenvalues of Lz will turn out to be 1, 0 and minus 1. Okay? And you can also find out what is Lx square plus Ly square plus Lz square. You take this as an exercise. You work out Lx, Ly, Lz, find out Lx square plus Ly square plus Lz square. Square of the matrices. All the squares will turn out to be identity matrix. You will find that Lx square plus Ly square plus Lz square is equal to what? Huh? Yes. Be bold, tell me. Huh? No. Well, there is a factor, small factor which is in front. You will find it to be equal to L into L plus 1, where L is 1 now. 1 0 minus 1 I said. So, it will turn out to be 1 into 1 plus 1, which is 2. The answer is 2. Okay? You will find it to be 2. So, what you are having is, which I am going to show, the values for L square are going to be L into L plus 1. The allowed values for L square are L into L plus 1, where L square is Lx square plus Ly square plus Lz square, and the values for Lz, which are also diagonalized. You can diagonalize any matrix. You diagonalize for the general convention because it matches with spherical polar coordinates, Lz, you will find it to be minus L to plus L, minus L plus 1 and then minus L plus 2 till you reach plus L, right, minus L plus 1 till L plus 2 you go up to some value which is plus L, that is all. So, there are 2L plus 1 values for that. So, this is what is the thing is. So, I have given you explicitly one representation of L is equal to 1, because we know these are all rotations in 3 dimensions. Okay. The matrix, the representation which I have given you in the parlance of group theory, it is called the fundamental representation, what people call as a fundamental representation, or in this case it turns out to be what is called adjoint representation. These are all only words, you can forget it. So, this is what is the structure. Given this, I am going to look at the angular momentum theory briefly. So, what is it you have to do is, I have, let me call Li Lj or sorry Lx Ly is I Lz, Ly Lz is I Lx, cyclically Lz Lx is I Ly. These 3 objects, that is what your R cross P is, and this is the thing. What are the sizes of the matrices which you can find for Lx, Ly, Lz? Already I have found one. I have found already one, okay, which is the 3 by 3 matrix. 3 by 3 matrix is explicitly I found for you, right? It is only rotations. So, can I find something more? Can I find for L is equal to 2, L is equal to 3, L is equal to 4. So, L is equal to 2, what will be the size of the matrix? What will be the size of the matrix? L is equal to 2. 5 by 5 matrix. You all agree or you disagree with him? He seems to be a nice guy. He says it is 5 by 5 matrix. Do you agree or disagree? Or you do not have any opinion? What is your vote? Yes or no? Huh? Please tell me. I do not want to lose all of you. He says L is equal to 2, means it is a 5 by 5 matrix, right. So, many heads are doing this, which I agree, they are all agreeing, and rest are keeping quiet. It is 2L plus 1 dimension, 2L plus 1 is 5 dimension, and he is right, okay, 5 by 5 matrix. So, you should find Lx, which is 5 by 5 matrix, you should find Ly, which is 5 by 5 matrix, and Lz, which is 5 by 5 matrix. Okay? These are the ways in which you should find the matrices. Now, if L is equal to say 3, what is the size of the matrix? 7 by 7 matrix, which means you should find a 7 by 7 matrix of Lx, you should find a 7 by 7 matrix of Ly and 7 by 7 matrix of Lz. Correct? That is what you should get. Perfectly right. Now, this is the way in which people find what are called explicitly. In group theory, they call it representations. Representation for L is equal to 1, representation for L is equal to 2, etc. Okay? Now, I will give you, I have already given you this matrix. Whatever I wrote here, Lz, I wrote here I minus I 0. This is the matrix I wrote. Similarly, you can write for Lx and Ly. Okay, you can write, and that will satisfy all the three equations. Okay, all the three equations it will satisfy. You agree with that? Now, I write a new matrix. I will call this as Lz1. Okay. Now, I am going to ask Lz2. That matrix is Lz1 0 0 Lz1. I have written here. Similarly, Lx2 Ly2, and this is simply Ly1 0 0 Ly1, and similarly for Lx and Ly, right. This is x here, and similarly for this. I have given what is called 2. What is the dimension of that matrix? What is the dimension of that 2, Lx2 or Lz2? Huh? What is the dimension? What is it I have done? I have put only the same matrix here and here, that is it. I have taken Lz. Anyone has an answer? How is it 5? This is 3 by 3 matrix. This is 3 by 3 matrix. This is 3 by 3 matrix. No, 6. It's only 6, which has one block on the first and the second block in the second thing. So it is like this. This block is, this is one block and this is one block. Everything is L here, the same L. So it's a 6 by 6 matrix, right? Is that agreed? Will it, this new L2, will it satisfy those equations? Right? It should satisfy. It is simple. I have not done anything, right? I have not done anything. I have only put 2 of the same thing. Okay? I have put 2 into 2 4 and 3 into 3 9 and then put 2 as a matrix. There is nothing. So, you have not generated anything new. Okay? You are having the same representation which you have written in many blocks. Now, this kind of object in group theory is called reducible representation. It is called reducible representation. Okay, you can block diagonalize it. You can make it into 2 blocks, each one of them, and each one of them satisfies that equation. So, that is not giving you anything new. It is only what you know already, is you are putting it in different blocks. So, this is reducible. So, what I want now, I can ask the question, can I make this Lx, Ly, Lz which I have given, block diagonalize it? Can you do it? Well, you cannot do that because Lx will involve these 2 and Lz involves these 2 and Ly will involve these 2, okay, first and third. Okay. So, they mix all the 3. There is no way you can write it as block form, all of them in the same block form. So, that representation is called irreducible, you cannot reduce it further, you cannot reduce it further. I am trying to teach group theory without actually using the words group theory, okay. I am trying to give you the same thing which is there in group theory by using words which are there, which is only matrix representation. So, this is basically the idea, okay. Yes. It is only LZ2 is only LZ1 in 2 blocks. Okay, it is the same thing appearing in one block here, another block here. It is block diagonalized. Okay, block, every block satisfies the equation, so the whole thing satisfies the equation. That is all I am saying, right? Okay. So, what we want is set of all irreducible representations, set of all irreducible representations. Okay. Now, there are ways of constructing it, but I will try to do some physics ways. I told you Lz is a angular momentum, magnetic quantum number along z axis, and the values are 1, 0 and -1. Okay. It corresponds to angular momentum L is equal to 1. L is equal to 1, magnetic quantum number is 1, 0, -1. Okay. Now, I take, so there is a magnet or there is a spin with spin 1, and then it can point along z axis with +1 or -1 or 0. These are the 3 values allowed. Now, I take 2 such objects. What are the angular momentum of the composite of 2 objects? What are the angular momentum? So, first one is also, second one +1 will go to 2. Okay. Similarly, -1 along with -1 will go to -2. 1 and then the 2 and -2 are easy. Now, then I do this object. The first one is 1, the second one is 0, right? Second one is 0. What is the total value? It is 1, right? 1 plus 0 is 1. So, you can have 2 and then 1. I can have both of them to be 0, then 0, then I can have -1 and 0, which is -1, and -2, but -1 and -1, which will give you -2. Okay, this is what I have done here. I will try to draw the diagrams. 1, 0, -1. I have 1, 0, -1, 2 such objects. I can go to 2 by having both of them 1. This and this I can go to 1. This and this also will give to 1. And then I can go to 0 by 0 here, 0 plus 0, or I can go to 1 -1, which is also 0, and -1, 0, which is also 0, and then I can have -1 with 0 will give you -1, and -1, 0 and -1 will give you -1, and then -1 with -1 is -2. Right? This is what I will get. If I have 2 composite of 2 spin 1 particles, spin 1 objects, if I have composite of 2 spin 1 objects, what will you get? You will get all these states. Now, what are these states? What are these states? It starts from 2, 1, 0, -1, -2. That is what you called as angular momentum L is equal to 2. It will have 5 states. Angular momentum 2 is 2, 1, 0, -1, -2. So, this is, I will call L is equal to 2. I will call this as L is equal to 1. I will call this is L is equal to 1. This is L is equal to 2. Okay? Now, what are these things? What are these things? L is equal to 1. So, and what is this? L is equal to 0. So, when you have a composite of two spin 1 objects, you will have a spin 2 object, you will have a spin 1 object, you will have a spin 0 object. Okay, this is what is the thing. Now, when I say spin 2, spin 1, etc., I should be able to write down, when I write down a matrix for this combination, okay, I should be able to get a spin 2 object in it, spin 1 object in it, a spin 0 object in it. Okay. So, now what is the dimension of the composite object? The composite object consists of both. There are 3 states here, there are 3 states here. The composite will have, everyone hesitates to say, even if it is wrong, tell me. 9 states will be there, right? Because it can be any combination. I goes from 1, 2, 3, 3 states. J goes from 1, 2, 3. Ij will go from all possible ways, 3 into 3, which is 9 states. So, this composite object will be a 9 by 9 matrix, Out of this, this is the 5 by 5 matrix, this is a 3 by 3 matrix, and this is the 1 by 1 matrix. So, you are able to write that as 9 by 9 matrix in the form of 5 by 5 matrix, 3 by 3 matrix, and 1 by 1 matrix. Now, you know only already L is equal to 1, I construct the matrix. By this process, I can get L is equal to 2, because that 5 by 5 matrix I can easily work it out. How do I work out? That is another one which is there in what is in matrix theory. In matrix theory, you have a matrix A, let us say it is M by M matrix, and another matrix B, which is another M by M matrix. You get a matrix C. What is the matrix of C? It is again 3 by 3, right? You take the row and column, that is what you do, and that is what you are getting. Now, there is another product which you can take, okay? This is what is called matrix product. Another product which is called direct product, and it is written as A cross B. Okay, I will tell you the rules for that. I do not know whether you are aware of it. I will tell you the rules for it. Here. I will tell you the rules for it. What you have to do is the following. I will tell the rules with some simple example. A is a 2 by 2 matrix. We will have A11, A12, A21, A22, right? A 2 by 2 matrix. Incidentally, in AB cross C, AB is equal to C, the number of columns in A should be equal to number of rows. That is what needed. N cross M, you can even a rectangular matrix N cross M, you can multiply by M cross P, but that M should be equal. How? If there are something like so many rows, the column should be exactly equal, otherwise you cannot multiply. That is the rule, but generally we multiply square matrices of the same size, there is no problem. But here I am going to multiply A cross B, where B is a 3 by 3 matrix. A is a 2 by 2 matrix, B is a 3 by 3 matrix. Now I will tell you the rule for A cross B. I will tell you the rule for A cross B. First of all, in this case, A cross B will turn out to be 6 by 6, the 2 into 3, 6 by 6 matrix. I could have started with both are 2 by 2 matrices, in which case it is a 4 by 4 matrix. You will have a 4 by 4 matrix, but just wanted to make life a little more difficult for you by having a different size matrix. Okay? So, what is it you have to do? A cross B is A11, so this is that thing, A11 multiplied by B, A12 multiplied by B, A21 multiplied by B, A22 multiplied by B. Remember, B is a 3 by 3 matrix, right? For your benefit, I am going to write only A11B for this alone. Okay? This alone I am going to write. You can write the same way this all the three. It is A11 B11, this one, A11 B12, A11 B13, A11 B21, A11 B22, A11 B23, and then A11 B31, A11 B32, A11 B3. That is that first term, first block. Okay? That is a rule for what is called the direct product of two matrices. Direct product of two matrices. That is what you have as a rule. So, what you are doing, as I told you, how many, what is the dimension? It is 2 into 3, which is 6. If I had multiplied a 3 by 3 matrix with a 3 by 3 matrix, direct product. If I had multiplied, what will be the size of the matrix? 9 by 9. So, that is what I did in the previous example. This example which I have done here, I have taken this matrix, I have taken this matrix, I have taken the direct product of those two matrices, which is what I have constructed the 9 by 9 matrix. But that 9 by 9 matrix, okay, I have constructed in such a way that it is a spin 2 block, spin 1 block, spin 0 block, say 5, 3, 1, right? That is the way I have constructed. That is what is the, okay, forget all these things. So, now I am going to give representations of all other thing, a simple way in which it can be obtained. Some of these things are there in regular textbooks, so I am going to be minimal about it. Is there any question? Any question? Okay. I think I am doing very well. That is why nobody has questions. Okay. I will start with LZ and L square and LZ are diagonal for B. Both are diagonal matrices. So, which means to specify this, I will have L, I will specify this with M, and I will call that as M, L, comma M. Okay. What is the meaning of this notation is, it is a column vector. Different eigenvalues of M, LZ, okay, in that basis, diagonal basis, I write this thing. This is the standard notation in quantum physics. What they use the ket notation. Ket to tell me it is a ket vector. It is a vector which is a column, various values of M which is there. So, like 1, 0, minus 1. For example, let me write for your benefit, um, L with plus 1 is actually this state. This is the vector. L with minus 1 is 0, 1, 0, that vector. And L is equal to, sorry, M is equal to, M is equal to, M is equal to 0. And then M is equal to minus 1 is 0, 0, 1. Okay? This is the meaning of this object and this object and this object. So, I will write this notation. You did earlier harmonic oscillator where you have the ladder operators A dagger and A. Similarly, I will have ladder operators which is 1 by root 2 Lx plus Ily and 1 by root 2 Lx minus Ly. These two are ladder operators. Why are they ladder operators? They take any state with value m, it goes one step above m plus 1 or m minus 1, okay, m plus 1 or m minus 1. Yes, any question? So, it is a ladder operator. It is almost like, for example, in Hermite polynomial, you are multiplying a polynomial with x power n, it goes to x power n plus 1. You differentiate with respect to d by dx, it goes to x power n minus 1. So, one power is increased, okay, one state is increased, that is what is the thing. Same thing is happening for A daggers, etc. Here also the same thing is happening using the fact that you can work out, take it as an exercise, what is Lz with L plus minus. Take it as an exercise, Lz with L plus, you can work out with Lx, L plus is Lx plus Ily. So, what I am asking you to work out is Lz with Lx plus Ily. What is on the right hand side? I have already given the commutation relation, you are already having that, okay? And Lz, Lx minus Ily, both of them. You find out for both of them, you will find very interestingly, I will give you probably the answer, it will turn out to be plus or minus L plus minus. L plus will take one step above, L minus will take one step down. It is a ladder, right? L plus will take one above one thing. It is very simple to work out. Now, what is the, I think there should be probably a factor of I also, you can work out. You check, this is probably a factor of I. Okay. Now, the interesting result is, if you have a state with m, if you have this state with m, Lz with Lm is m times Lm. Now, you can ask L plus acting on Lm will give me a new m prime, it will give me a new state, because it is not an eigenstate of Lz, right? It is not an eigenstate of Lz. This it will be it will give me a new state m to m prime. It is not an eigenstate of this, there is no eigenvalue equation here. It will turn out this is an eigenstate of Lz. It will be an eigenstate of Lz using this relation. Using this relation, you will find Lz acting on L plus Lm is equal to m plus 1 times L plus Lm. That is, this whole thing is a new state m prime, and this thing is an eigenstate of Lz. L plus acting on m gives me a new state. That state is also an eigenstate. Same thing happened for harmonic oscillator. You had n, the state n, a dagger acting on that gives you a new n prime, but it is an eigenstate of a dagger a, okay, number operator. So that's what happens here. So what you start with m, some value, by L plus you can go up one step. You can go one step. Now you operate again on this, you will go one more step like this. You will keep on going by L plus acting on that somewhere, right. Now unlike the case of harmonic oscillator, for this case it should stop at some point. It cannot go on, and that is very simple result coming from the fact that Lz cannot go beyond L. The eigenvalues of Lz cannot go beyond L, okay, the value L which you started with, where L is connected to the L square. L is connected to the L thing. How do I know it? How do I know it is from this thing. For me, Lx is a Hermitian operator. Lx is a Hermitian operator, which means it will have only real eigenvalues. When I say real, it can be positive and negative. It can be positive and negative, okay, positive and negative. Now if I take Lx square, Lx square eigenvalues are, if you have A has eigenvalues A1, A2, A3, square of that will have A1 square, A2 square plus A3 square. That is all. The square of eigenvalues, square of a matrix has eigenvalues whose square of the matrix itself, the only thing, as simple as that. Because you can diagonalize it, and then when you diagonalize it, you will have only square of that. So this is what you are going to have. This object Lx square will have only, will it have negative eigenvalues? It will not have any negative eigenvalues. That kind of matrix is called positive definite matrix. If all eigenvalues are positive, it is positive definite eigenvalues. Similarly, Ly square is also positive thing. It will have only positive eigenvalues. Now L square we know is Lx square plus Ly square plus Lz square. L square is also positive, okay. Now I take this Lz here, L square minus Lz square is equal to Lx square plus Ly square, correct? It's simple relation, which says L square minus Lz square should be positive, which means Lz square cannot exceed L square, right? It cannot exceed L square, otherwise it will become negative, right? It will become negative. So Lz is bounded, Lz eigenvalues square is bounded by L square. It cannot go above that. But I was just giving you that I start acting on m, I go to m plus 1, m plus 2, etc. Beyond some value, it has to stop. Otherwise, it will not obey that. So that place where it stops, I will call it as L plus L, and m is equal to, it stops at m is equal to L, is 0. That state annihilates that. It is a state which is annihilated by that LZ matrix, L plus matrix, L plus matrix. So, you start with m is equal to some value like say 4 or say 1, you may go up to 2 and then 3 and then that is it. L plus acting on that has to be 0. Similarly, L minus acting on Lm will give you new m double prime, and L plus Lz acting on L minus L min will be equal to m minus 1 L minus Lm. So, what is L minus is doing it? Instead of going up, going down. Okay, it is like there is a 30-story building, you are in the 10th story. If you take the lift, you can go to the up, you can go up or down. That is what is happening here. That is why it is called ladder operators. Okay. Again, by the same arguments, it cannot be lower than some value. So, at some value, it has to be annihilated by the same argument. It turns out very easy to prove that the value will go from minus L to plus L. Minus L to plus L. The m value will go from minus L to plus L. You start somewhere in between any value, acting by L plus again and again, you will go to the highest value. Acting again and again by L minus, you will go to the lowest value. And the number of values is from minus L to plus L, which is, if they are integers, you know the number of values will be 2L plus 1. You take any number 5, you start from minus 5 to plus 5, how many integers are there? Okay, that is all, 2L plus 1, as simple as that. Now, with all these things, I am going to, I am speeding up, I am trying to give only the gist of the thing, little more details I can work it out, but that is what is done in any class in quantum mechanics, quantum theory. Probably those of you who have not taken quantum classes will find it the same thing repeated with little more calculations done. Those who have taken up quantum mechanics classes, you might have seen it already. So, I will give you the answer, because I want to go to at least something new beyond what is going to be taught or what is already taught in quantum mechanics classes. Okay. So, Lz is going to be a diagonal matrix. So, it is going to be Lz, the state is labeled by this object m times Lm, L square acting on Lm is given by the value is not is L into L plus 1 times L comma m. Now, I should tell what is L plus acting on Lm and what is L minus acting on Lm. That will give me all the matrices. All the matrices which you know, these are all diagonal matrices. This is identity matrix. This is identity matrix with eigenvalue L into L plus 1 diagonally. All of them are same. This is not identity matrix, but diagonal matrix. It is a diagonal matrix. For example, we had 1 0 minus 1, L square will be 2 into 1 1 1, this is L square, this is Lz, and I should tell you what is L plus, L minus as a matrix, 3 by 3 matrix. Okay? I have already given you what is Lx and Ly in that case. You can simply add Lx plus ILy, that will give you L plus and L minus, right? That is nothing new. But anyhow, I will give you the answer for arbitrary L. I will give you for arbitrary L, any L. For any L, the answer is the following. L into L square root of L into L plus 1 minus M into M plus 1. So, plus or minus here, that is it. And then the state is not an eigenstate, so I should get M plus or minus 1 here. Acting on the state Lm, L plus will give you L M plus 1, L minus acting on that will give you M minus 1. There is a coefficient which will come because the state should be normalized, okay? It should be normalized. So, if you want to, if you start with Lm is normalized, that is a norm of the vector is 1, that is M comma M prime, the two states, integral is equal to 1, then this is additional normalization you will get. Okay. So, this is the result actually. So, I realize my M plus 1 has gone outside, so be careful. So, it looks like whatever I write here will not be seen there, is it? Whatever I write here is not seen there, or they change the camera, I do not know. So, I will you please, you have to let me know because I realize only now. Okay. So, I will write it at least. That is it. Okay. So, that is your angular momentum. That is your angular momentum, and we have already worked out 3 by 3 matrix. 5 by 5 matrix is easy to write down. Now, you put L is equal to 2 and M is going from minus 2, minus 1, 0, 1, 2, you will get 5 by 5 matrix. You can do for any number which you want. You can put even million. If you are capable of doing million by million matrix, you can do that. But what we need is 0, 1, 2, 3, not even 3, 0, 1, 2 is enough. Okay? That is the kind of thing which you have as what I called as representations of angular momentum algebra. There is a name for it. Whatever is written is called generators of the angular momentum, which is called Lx, Ly, Lz. They obey an algebra. Then the technical words are they obey an algebra, which is what I wrote to you earlier. Lx, Ly commutator is I, Lz, and the 3 commutation relations, and the representations of that algebra will be given by such matrices. Okay, it is called, that is as simple as that. Okay, if you what this generator will do for you is, once I have this, once I have Lx, Ly, Lz, I can take e to the power I theta times L, that matrix, which means theta 1 time theta x, let me write explicitly. If you take theta x Lx, theta x Lx plus theta y Ly, theta z Lz, okay, that will do the transformation for arbitrary rotations. For arbitrary rotations, what does the Lx, Ly, Lz tell you is for small rotation, infinitesimal rotations, what is the change? This is the difference between, if you know what is infinitesimal, you can easily exponentiate to get the full glory arbitrary transformation. Is that clear? Yes or no? So, that is what is done everywhere. Now, the value of L is 0, 1, 2, all integers. In mathematical notation, that is that Z people write. Okay? The integers. That's what any value you have the matrix. Any value you like. Okay? That's what is the way in which you have. Okay? That's why in hydrogen atom, the same thing is coming for L, for that L value is restricted by principal quantum number n. It cannot go beyond n. So, n should be less than L. L should be less than n. But n can go up to infinity. It can go over 1, 2, 3 up to large number, which means L can also go up to large numbers for the corresponding value. Higher and higher orbits will have higher and higher angular momentum. This is what you have here. Now, I can do one thing now. I have to introduce something new, and that something new is what you learn from hydrogen atom or electron. What you learn from electron. The electron has orbital angular momentum in hydrogen atom. If you remember, it is NLM. N is the principal quantum number, L is angular momentum, M is magnetic quantum number. That is what you are taught, right? All of you are taught this three things, and the N is going to be 1, 2, 3 up to infinity. L is 0, 1, 2 up to L, up to N, n minus 1. M is minus L to plus L, minus L to plus L. This is what you have. Okay? But electron, as funnily, has a spin value. That is what we realized. The electron, even at free stage, when the free electron is there, it can be spin up or spin down. How do we know that it has spin up and spin down? I don't know whether you have heard of this famous experiment called Stark effect. You have a bunch of electrons coming, and then there is a magnetic field which is applied. The spin up electrons go up and spin down electrons go down, and you will make a point on the cathode ray oscilloscope on one side and here. That is what happens, which means the bunch of electrons can exist in two different states, and the two different states we call it as spin up and spin down. Two states. If the thing is corresponding to angular momentum, what is the spin value of that? Two states. I said 2L plus 1, right? 2L plus 1 equal to 2. If 2L plus 1 is equal to 2, 2L must be equal to 1 and L must be half. We call it spin angular momentum, spin value, which is half, spin half, spin half. Spin half will have spin up and spin down, or half plus half, which is called 1 0, 2 by 2 matrix, minus half is 0 1. This is spin up and this is spin down. Okay? This is what is there. I suppose I am going outside slowly. Be careful. So, you have to tell me when I am going outside. So, this is what you have for, yes? So, this is what you have here. I think I probably should stop with here, somewhere here. I will put it. Okay. Because he has fixed the camera and gone. Okay. So, if there is a spin half representation, I should be able to give the L plus, L minus and LZ for that. Okay? L plus L for that. Okay? So, I am going to give that. So, I can work out, let me call it as SZ, because it is spin. Instead of LZ, I will call it as SZ. It will have spin up and spin down values, and that matrix which is diagonal, and I will call it as half 1 minus 1, right, half and minus half eigenvalues. There is a name for this matrix. There is a name, this is called half sigma z. People call it as Pauli spin matrix sigma z. Similarly, I can have S plus, S minus. I have given you the formula. What is L plus acting on this thing, right? From there you can work out what is S plus minus. That will turn out to be half, is going to be half sigma x plus I sigma y and plus or minus. Now, what is sigma x and sigma y? Sigma x is going to be 0, 1, 1, 0, and sigma y, if I am right, it is going to be I minus I. There might be a minus I also is possible. Okay? So, that is what the three matrices, sigma x, sigma y, sigma z, which are called Pauli's sigma matrices. Pauli's sigma matrices. The angular momentum, spin angular momentum is half times sigma. Half is the number associated, plus half and minus half. So, this is what is the thing here. So, if you look into that definition which I have given you for angular momentum, it works very well even with half. So, it allows value for the half value. It allows for the half value. It allows for half value also. Okay? Now, what is the difference between integer and half integer? Why is it you do not have in hydrogen atom? Hydrogen atom has only orbital angular momentum. When it rotates around, like Earth rotating around Sun, it has only integer values. But the spin part of it, which you can imagine it to be rotating about itself, there is no truth in it, but rotating about itself, it has a plus half and minus half, and that is given by this. Okay? Is that clear? This is a fundamental difference. The fundamental difference is the following. So, you start with some spin up state 1 0, okay, 1 0 state. If you are rotating about z axis, just z axis, the generator for that is sigma z. So, you will calculate I sigma z by 2, because the generator is I by 2. Generator is sigma z by 2. Sigma z is not the generator, half of that is generator. You should remember that factor of half. If you have that, sigma is it, when 1 plus I sigma will give you small rotations. If you do small rotations, if you do large rotations, this is what you have to compute. This is what you have to compute. If you do large rotations, you should exponentiate. If you were exponentiating for orbital angular momentum, you should do it here also. If you do that, it will turn out to be, take it as an exercise, expand it, and the interesting thing is all the sigma x square is equal to sigma y square plus sigma z square is 1 identity matrix. You can easily work it out. You can even find out the algebra of sigma matrices, which is using the factor of half. Remember half. So, that is the way you should work it out. If you do that, I have taken only a simple example here. You can do arbitrary angle also. This will turn out to be equal to, the matrix is cos theta by 2 plus I sin theta by 2 cos theta by 2 minus I sin theta by 2, 0, 0 multiplying 1, 0. Yes? So, this is what you have here for this object 1, 0, etc. So far, so good. Now, I rotate my z axis. I rotate my z axis about z axis by an angle 2 pi. That means, this is my z axis. I rotate this whole room about this axis by 2 pi. So, you have come back to the same point. You have come back when you do 2 pi rotation. Now, when I do 2 pi rotation here, this one cos pi by 2, this is sin pi by 2, 0, etc. You will find it does not come back to its original value, because theta by 2 is there. It is not theta. Cos theta 2 pi is same as cos 0 is same as cos 2 pi, but cos pi is not, cos pi is fine, but sin pi. So, cos pi by 2 for example, because pi by 2 if you do that, or cos pi and sin pi if you do, there will be differences, the sign differences will be there. So, what has come is, if I do 2 pi rotation, I do not come back to the same value. If I do 4 pi rotation, then you come back. The state, okay, the state has become, when you do that rotation 1, 0 or spin up, go to minus this thing and then come back. Okay, that is what happens in the case of spin half particle. 2 pi rotation does not bring it back to the original value, whereas it will do for integer angular momentum. There is no problem for integer. Whenever it is half integer, then 2 pi rotation will not bring it to itself. So, these representations are called, the name for that is spinorial representation, whereas the other ones are called vector representation, vector, tensor, etc. Whereas spinor representation, under rotation 2 pi, you do not get the same state, but negative of that state. Okay, if you start with 1, 0, you will have minus 1, 0. That is what you will have. Okay. So, this is the beauty of spinorial representation as compared to vector representation. Now, that is where my final punchline is going to be. After that, I will tell something more. The spinor, like electron, has spin half particle. Okay. You might be taught, I do not know, in statistical mechanics classes somewhere, this kind of electron behaves like fermions, which means if I take wave function for 2 particles, psi 1, psi 2, the wave function for 2 particles we will write it as psi f 1 comma 2, or let me write 1 comma 2, or phi 1 r1 r2 for 2 particles. Okay. And the 2 particles are identical particles, you cannot distinguish them. It is a very important concept, identical and indistinguishable particles. If you have an electron here and another electron here, you put this electron here and this electron there, that state is identical to the previous one, you cannot distinguish it. Okay? You cannot, two electrons are identical and indistinguishable. Now, if I exchange 2 particles, you expect it to be psi of r2 comma r1. Okay, the wave function will be psi of r2, which is equal to the old value. This is what you expect. This is what you expect. It turns out there is a minus sign. It turns out there is a minus sign. For, and without that minus sign, your atom cannot be stable. That minus sign is coming from the fact Pauli's exclusion principle, which says that you cannot put two electrons in the same state. If you have two electrons in the same state, the probability for that should be 0, which means in the hydrogen atom, in the ground state where n is equal to 1, you can have one electron. If you want to put the other electron, you have to put, if it is spin up, this should be spin down. Now, if you want to put the third electron there, you cannot do that. In the ground state, you cannot do. You have to go one step above. N is equal to 1, 2. You have to go. Then, how many electrons can be there in n is equal to 2? You can have n is equal to 2 means L is equal to 0, comma 1. Right? L can be 0, comma 1. In L is equal to 0, comma 1, again the 0 can be spin up and spin down, and 1 can be 1, 0, minus 1 and spin up and spin down. So, total number of electrons in the first, other than the ground state, one excited state, is going to be 8 electrons. So, the first orbit ground state will have 2 electrons, then it is full. The room is full, you can't put anything more there. When you go to the next thing, you are going to put 8 electrons. After that, it is full. You have to go above. When it is full like 8 electrons, when it is full like 8 electrons, it doesn't want to interact because it doesn't want to admit any other fellow. Okay? So, they are the inert gases. In chemistry, you will find they are all the inert gases which come about. So, the Pauli's exclusion principle helps in understanding the chemistry table, Mendel's table of what are the stable elements and what are the things which interact. Sodium will interact with chlorine or sodium chloride, etc., because you cannot put, if this is one electron down and that is one electron can accommodate, they will join together. There is a room here and there is a person, extra person there. So, they can join together. So, like that it happens. So, this leads to this profound principle which was used to explain the stability of atoms, which is called Pauli's exclusion principle, and fermions obey Pauli's exclusion principle. Pauli's exclusion principle. Fermions obey Pauli's exclusion. Now, this famous theorem, and the theorem is spin statistics theorem. Any integer spin particle obey bosonic thing, that is plus 1. Any half integral particle obey the fermionic particle. There are only two kinds of particles. One is bosons, another is anions, fermions. These are the two things, and that fundamental nature of this thing comes from the theory of angular momentum with half integral values and integral values, which is allowed in the case of this thing. Now, I have this last question, 2 minutes is there in my watch. Is that okay? Okay. So, I told you in the case of two-dimensional oscillators, two-dimensional oscillators, you have the states are, the ground state is n is equal to 0, n comma m, 0 0, degeneracy, there is no degeneracy, one state is there. The next one is 1 0 comma 0 1, there are two states. The next one is 2 0, 1 1 and then 0 2, there are three states and so on. Okay? It goes in the same form as that, which seems to match with angular momentum theory, right. So, there is some angular momentum which is coming there, but unfortunately that angular momentum is mysterious, because that angular momentum which you expect, if at all there is a two-dimensional harmonic oscillator, you can do rotation about xy plane. You do not have z plane to rotate, you have only two, right. How does a three-dimensional angular momentum come in this thing? Okay, that is the question. some of you should think about it, and but I can give you one clue, and that clue is there are two oscillators, which is p square plus x square, px square plus py square plus y square, half of it. This is your Hamiltonian, which I can have an creation operator here, A dagger A and A dagger. For this I can have B dagger B, this is my Hamiltonian. So, you have two creation operators and two annihilation operators, A dagger A dagger, B dagger. What is the commutation relation? A dagger is equal to 1, B dagger is equal to 1. Now, I will give you, you can work it out, this is another exercise. You construct A dagger B, A B dagger, and then A dagger A minus B dagger B. I will call this as Lx, and this L plus, L minus, and Lz. I will call this way, okay. Construct the commutation relations between these three objects, A dagger B, A B dagger, and this, and probably a factor of half. Okay. You construct that, unfortunately it will turn out to be exactly your angular momentum algebra. Okay. And that is an exercise you can report to me by tomorrow morning or today evening. I am going to stop here. My friend has come from the IIT, so I have to respect him. Okay. If there are any further questions, I am available during coffee time and also in the afternoon for some time. Sorry, some telephone. Okay. Any further question? Fast question anyone wants to ask? Okay, I will stop here.
Okay. So I can put here. It's already on, right?
Valid.
Hello, check. Yeah, please.
Okay, sir.
Okay, thank you.
Welcome to the first Alladi Ramakrishnan centenary lecture by Professor Ashok Sen of ICTS. I'm here just to make a few opening remarks. I'm Krishnaswamy Alladi, son of Alladi Ramakrishnan. The proposal to have a lecture series of this type was made in December 2023 during the Alladi Ramakrishnan Centenary Conference that took place here at IMSC. And when I made this suggestion, the director, Professor Ravindran, and the organizers of that conference very enthusiastically endorsed this suggestion and said, yes, we will proceed with having this lecture series. Just to give a little background, it is perhaps no exaggeration to say that the seminar spirit in Madras, or even in South India, was perhaps introduced in its significant form by my father, Alladi Ramakrishnan, not only in terms of what he did at the University of Madras, but in terms of what he did at our family home, Ekamarnivas, when he invited so many visitors, and that was the theoretical physics seminar that led to the creation of this institute. And he had luminaries come and speak at the seminar and also talk to the students. So that is first the background. And then after my father retired in 1983 as the director of math science at the age of 60, he continued to hold lectures at our home under the auspices of the Alladi Foundation. And again, very top people came and spoke, like Professor George Andrews, the Ramanujan expert, Michelle Waldschmidt, who comes and visits math science regularly, and so on, many people. After my father passed away in 2008, I continued this practice of having these lectures, but then I called them Alladi Ramakrishnan Memorial Lectures. And I just mentioned the first two. The first was given by Bruce Burnt, another Ramanujan expert, and the second was given by Professor C.R. Rao, one of the most eminent statisticians in the world. But I think really the venue of these lectures should now be at this institute, which has grown in stature and reputation in the last few decades. So I'm very, very happy that this lecture series is now held here, and especially happy that the opening lecture is going to be given by a very distinguished scientist, Professor Ashok Sen. And to introduce Professor Sen, I invite the director, and let me also just say that perhaps the best way to pay homage and remember my father is through a lecture series, because the very mention of Alladi Ramakrishnan's name brings to mind the seminar spirit. Professor Ravindran.
Very good morning. On behalf of Institute of Mathematical Sciences, warm welcome to Professor Ashok Sen and every one of you in this audience. It is indeed a genuine honor and privilege to introduce titan of theoretical physics, Professor Ashok Sen, to this august audience. I have the privilege to introduce him to you. Of course, most of you know about him, but of course, for the younger part, younger part of this audience, those who have, just started, doing science, this introduction is mainly to them, because we all know what Professor Ashok Sen has achieved. Born in Calcutta in 1956, Professor Sen's journey into the intricate world of physics began with remarkable start. He earned his bachelor's from Presidency College in Kolkata and his master's from IIT Kanpur, inspired by brilliant minds like Amar Kumar Raichaudhuri. From there, he pursued his PhD at Stony Brook University. Some of his colleagues are here, actually, his colleagues when he was a PhD student. They have all come here, setting the stage for a career that could profoundly impact understanding of our universe. Professor Ashok Sen is renowned for his groundbreaking contributions to string theory. Of course, he has contributed to many other areas of physics. A field he shaped for decades. He is one of the, leading figures in that field that everybody knows. Many people may not know that he is not the only leading figure in that field. He is also leading figure in many other areas in physics where I am interested in. He was among the first to grasp the seemingly distinct string theories, or actually different facets of same underlying theory, a profound revelation that rightly earned him a breakthrough prize in fundamental physics that we all know. His landmark paper on S-duality was the game changer, fundamentally altering the course of string theory research by revealing deep connections between strong and weak coupling regions. He is also pioneer of the studies that involves unstable d-branes, formulating the famous sense conjecture that is, is every string theorist, every physicist keep hearing. On open strings, tachyon condensation, his work on rolling tachyons has been influential in string cosmology. Beyond this, his contributions to string theory and the entropy of external black holes have been pivotal, connecting microscopic string theories to macroscopic black holes and their properties, and offering crucial insights into gravity and quantum mechanics. Professor Sen's brilliance is not just his discoveries, it is his ability to tackle the most complex theoretical problems with elegance and precision. I am a witness to this, for several years actually, to learn physics from him. Questions that trouble us. If you listen to his talks or his presence in audience, most of the time it was evident actually. His meticulous approach and deep intuitions have earned him numerous accolades, including famous Dirac Medal, Batma Shri, Batma Bhushan, and a Fellow of Royal Society, nominated by none other than Stephen Hawking himself. Currently, Professor Ashok Sen is a distinguished professor at International Center for Theoretical Sciences, ICTS at Bangalore, and he holds visiting professorship at institutions like MIT and Korea Institute of Advanced Study. He continues to inspire, lead, pushing the boundaries of what is possible in theoretical physics. Beyond all this, he is a great teacher. You'll experience that in a moment. I am one of the persons who benefited from his teachings as a student, as a postdoc, as a faculty at HRA. Okay, so I have a one first-hand experience with that. Today, we are especially fortunate. I am particularly thrilled that Professor Ashok Sen will be delivering this inaugural Alladi Ramakrishnan centenary lecture here at IMSC on this day. This prestigious lecture series has been instituted, as Professor Alladi Krishnasamy mentioned, to honor the birth centenary of Professor Alladi Ramakrishnan, the visionary founder director of this institute, the very institute where we are all here now. This is organized by IMSC with the generous support of Professor Ramakrishnan's family. This annual series will feature eminent mathematicians or physicists with a format that includes a public lecture, followed by specialized seminars or whatever lecture for the members of the institute. It's fitting tribute to Professor Ramakrishnan's legacy to have someone of this caliber, Professor Sen's caliber, inaugurate this series. And please join me in giving warm welcome to Professor Ashok Sen. Thank you.
Thank you.
Okay, thank you. It's a great honor for me to be giving the Alladi Ramakrishnan centenary lecture, and I'm really thankful to have been invited for this. I also apologize that I have not prepared this as a public lecture, because that's not what I had the impression of this lecture, but hopefully it will not be totally out of reach for most of you, I am hoping. Let's see. Okay. So the lecture today will be on classical gravitational wave tails from soft theorem. Okay. So let's imagine that there is a violent explosion in space, okay, where some stationary system breaks apart into fragments. Now during this process we will have gravitational waves coming out of this explosion, and if we have some detector D that is placed far away, it will detect this gravitational wave as some kind of ripples in space time. And examples of such violent explosion is a supernova, for example, where a star just blows up, okay, sending out fragments into space. One can also consider a more general situation, okay, that involves collision of objects, okay, where a set of objects come together, interact, and then fly apart, and in that process they may exchange mass, they may exchange energy, momentum, and other things. This process will also produce gravitational waves. And one example of such a collision in our universe is what is called the bullet cluster, okay, which involves a supercluster of galaxies which pass through another supercluster of galaxies. Each of these weigh about 10 to the 14 times the mass of the sun, okay, and they move at a relative speed of about 1% of the speed of light. Now while we know that such processes will emit gravitational waves, okay, in general if you want to actually compute what kind of gravitational waves come out of this process, okay, it is a complicated computation, okay, and it is complicated because of two reasons. Okay. First of all, when the objects are close, they may undergo complicated non-gravitational interactions. Okay. For example, this is what happens in the explosion of a supernova, where the nuclear forces play an important role in the explosion. The second reason that it is complicated is because gravity is described by some nonlinear partial differential equations. Okay. So even if the interactions were purely gravitational in nature, okay, as for example in the case of black hole merger, okay, the analysis is still complicated because of the nonlinearity of the partial differential equations. Now this process is purely a classical process, okay, there is no quantum mechanics involved. Surprisingly, however, it turns out that some results in quantum theory of gravity, which are known as soft graviton theorems, can be used to get analytical results on some aspects of classical gravitational wave. And this will essentially be the focus of this talk. So before I describe how this is done, let me just mention my collaborators. Okay. So of them, two of them are from Chennai. In fact, Alok Ladha is a faculty member at CMI, and Arnab was a student at IMSC earlier. Now he is in Indian Institute of Science as a long-term INSPIRE faculty. Vishwajit Sahu used to be a student at Harishchandra Research Institute and currently a postdoc at the King's College. And Devanjan and Babli are beginning graduate students at ICTS. And a short review on this talk can be found in this archive paper. I should also say that much of the architect of what I am going to describe, at least in recent years, is Biswajit Sahu. Okay, he has been involved in almost all of these collaborations, and in fact has been the driving force behind most of the collaborations. Okay. And he also wrote several papers on his own and with other graduate students, which push the subject further. So let me set up the convention. Okay. So we will denote by c the speed of light. G will denote the Newton's gravitational constant. Now, in many of the physics talks, we sometimes set the fundamental constants to 1, okay, but I will not do this in this talk, at least for most part of this talk. Okay. So, all the fundamental constants will be explicitly in place. So, the space time coordinates will denote by this 4 vector x mu, where mu is this index mu runs from 0 to 3, x0 is c times t, where t is the usual time coordinate, and this is the usual space coordinates that we are familiar with. We will denote by 4 momentum p mu, okay, again a vector with 4 components, of which the first component p0 is energy divided by the speed of light, and these are the usual components of momenta that you are familiar with. Eta mu nu, both with lower index and upper index, are 4 by 4 diagonal matrix, okay, and the eigenvalues are minus 1 1 1 1. Okay, so eta mu nu you can think of as a 4 by 4 diagonal matrix with these entries on the diagonal. Given 2 4 vectors, okay, we will denote the dot product between the 2 4 vectors by this formula over here, okay, and because eta mu nu is a diagonal matrix, when we expand this out, okay, it takes this form. And in this spirit, p square, which is p dot p, okay, is given by this, okay, by the special case of this formula, and you can use the formula for p0, which is E over c, right, you get this, and then using the standard relation, relativistic relation between energy and momentum, we can show that this is just minus m square times the speed of light square, where m is the mass of the particle. We will use what is called the summation convention. Okay. So, if we have an index that is repeated in a given expression, okay, it is repeated twice, okay, then we assume that it is summed over, even though you do not write an explicit summation symbol. Okay. So, when I write something like this, it is understood that this is actually given like by this, okay, that is sum over mu from 0 to 3 of this, because the mu index has been repeated twice. We will raise and lower index, okay, by eta. So, if you have a vector with upper index, okay, a vector with lower index will be defined by the multiplication of eta mu rho, and the rho is summed over because it is repeated. Okay, I am not writing that anymore here because I am using this convention. Okay. And similarly, if you have a vector with lower index, you can define a corresponding vector with upper index by similar multiplication. Okay. So, using this formula as well as this summation convention, we can easily convince ourselves that these are the relations that you have between the lower index vectors and the upper index vectors. Now, let me come to gravitational radiation or gravitational waves. That's the object of interest in this talk. Okay. So, in general theory of relativity, right, which is the theory of gravity that is currently accepted as the correct theory, correct classical theory of gravity. Okay. A gravitational field is a symmetric 2 index field, okay, which measures the distortion of space time. Okay. And the precise definition of this 2 index field that I will be using is the difference between the space time metric, which measures distances in space time, and this matrix eta mu nu that I introduced earlier is the difference between g mu nu and eta mu nu divided by 2. Okay. So, in the absence of gravity, when h mu nu is 0, the metric is just eta mu nu, right. That is the significance of this metric, of this matrix eta mu nu that I introduced earlier. Okay. So, given this, okay, gravitational waves will involve space and time varying h mu nu, okay, and this is an exact analogy with electromagnetic wave, okay, where you have space and time varying electric and magnetic fields. or equivalently space and time varying electric vector potential. And the key distinguishing feature that distinguishes the radiation from static field is that if we are at a distance r from the source, then the measurable effects fall off as 1 over r and not as 1 over r square or faster. So, for example, many of you are probably familiar with electrostatic force, right. If you have a static charge and if you have another charge placed far away, the effect of the static charge will be felt by the charge that is placed far away through the electrostatic force, but that falls off as 1 over r square, right. So, all measurable effects for a static electric field falls off as 1 over r square or higher for, right, like a dipole, for example, will fall off as effect of a dipole will fall off as 1 over r cube. But radiation is different in the sense that at distance r from the source, the measurable effects fall off as 1 over r. And this is the reason why if you are sufficiently far away from a source, then the only part that you feel is the radiation, right. For example, we have probably many of you have heard of black hole merger, right. The way we know that there are black holes and which are merging is because of the gravitational waves that are coming out of it, because that falls off as 1 over r. Okay. They of course also have static gravitational field, right. The 1 over r square fall off, but that is impossible to measure, okay, because r is very, very big. Okay. So, our interest is in this quantity h mu nu, okay, but we will be defining another quantity which I will call E mu nu, okay, by this relation over here. Okay. This is just a convenience because the formula will be easier to write in terms of E mu nu, okay, but h mu nu can be reconstructed from E mu nu because given this we can easily show that h mu nu is given by the reverse relation of this kind. Okay. So, if I give you the expression for E mu nu, I can construct h mu nu and vice versa. And a gravitational wave detector like LIGO measures h mu nu. Okay. So, the goal of a theorist will be that for a given process we want to compute h mu nu at a far away detector. So, this is the general introduction. So, now what I am going to do is to summarize the results that we get, okay, and later on I will explain how we get those results, okay, but the first part of the talk I will take by explaining what the results are. So, let us again set up the general problem, okay, but in a little more detail. Okay. So, you want to consider the case of a scattering in space, okay, where you have a set of objects which carry 4 momenta p1 prime to pm prime. Okay, I have already introduced what 4 momentum means. Energy as the first, energy over speed of light is the first component, and then the usual momentum components are the last 3 components. Okay. So, you imagine that you have a set of objects which carry 4 momenta p1 prime to pm prime which come together, scatter, okay, and then go out as another set of objects with 4 momenta p1 to pn. Okay. Note that I have not assumed anything about the relationship between the initial and the final momenta, except of course the total energy and total momentum is conserved. So, when you add up all these 4 vectors, they should be equal to the sum of all these 4 vectors. Right. That is the only condition that we have, otherwise they can be completely arbitrary. Okay. So, you have a scattering taking place here, okay, and just for convenience we will choose a coordinate system so that the origin of space time is somewhere inside the scattering region. Where exactly it does not matter. Okay. So, when I say the origin of space time is in the scattering region, what I mean specifically is that the scattering takes place at some time of order 0, around 0, and at a spatial point which is at x vector equal to 0, right, origin of the space coordinate. Okay. So, once the scattering takes place, the gravitational waves are emitted, and imagine you have a detector placed far away. Okay. This wave will eventually reach the detector, okay, but of course there is a time lag because the gravitational wave propagates at the speed of light. Okay. So, it will take some time for it to reach the detector, but at some point the detector will receive that signal. And we call that time t naught. Okay. Again, the exact definition of t naught is not necessary. Okay. It is some time of so T naught is defined only up to some constant shift, right, because the wave takes some time to go through the detector. And our goal will be to examine the order 1 over r contribution to the waveform, okay, namely that we have this h mu nu which has a piece r inverse times some function of the direction in which the detector is placed, okay, and of course the time at the detector, because the wave, as the wave passes, the h mu nu will keep changing at the detector, okay. And then there are corrections of order 1 over r square that we will not be interested in, right, because these fall off too fast for it to be observable in any realistic situation. Okay. R here is the distance, and this n hat is a vector which tells you which direction the detector is placed. So we will define what we call the retarded time at the detector, right, which is the difference between the time and the T naught is around some value at which the signal is reaching the detector, right. T naught is defined only up to some shifts of order 1. Now what we will focus on will be the late and early time tail of the wave, okay, which means that the value of h mu nu at the detector at large positive u and large negative u. Okay. Now why should we focus on this? Okay. The reason that we will be focusing on these is because these are the quantities that you can calculate, okay, without having to go through complicated numerical evolution, right. As I said, all the complications that arise because of the gravity being non-linear, okay, and because there may be other interactions present, we will see that those complications can be handled if we look at the value of the gravitational field at large positive u and large negative u, which means that we are looking at the gravitational waveform, okay, at a time, okay, long before the major part of the signal reaches the detector and long after the signal passes the detector, right. So how the signal builds and how the signal falls is the part that we are focusing on. So here is the general summary of the result. It turns out that the terms that are proportional to 1 over r, right, this is what we are focusing on, if you recall, they have the following form at for large negative u, that means way before the signal, the peak of bulk of the signal has appeared, okay, and large positive u, okay, which means way after the bulk of the signal has passed the detector. So before the bulk signal reaches, right, the E mu nu starts building up, and the claim is, or the result is, that the E mu nu has an expansion of this form. The leading term in E mu nu goes as 1 over u, okay, where u is this time times some constant, then the next term goes as 1 over u square log u times this constant, and then there are other corrections. And similarly for far future, E mu nu has a constant piece, then there is a 1 over u piece, then there is a 1 over u square log u piece, and so on. Okay. So this is the first result, okay. But the more interesting part of the result, okay, is that these coefficients that you see, okay, are given solely by the 4 momenta of the ingoing and outgoing objects without requiring any knowledge of the details of the scattering process. Okay. So in other words, imagine that you have a set of objects coming in, colliding and going out. Okay. As long as you know what went in and what went out, okay, you can calculate these coefficients, okay, without knowing what actually transpired during the collision. Right. There may be nuclear explosion during the collision, or there may be purely gravitational effects, gravitational forces operating during the collision. All those are irrelevant. Okay. The result is given purely in terms of the momenta of the particles that went in and the momenta of the particles that went out. So the next two slides, okay, I am going to give you the expressions for these coefficients, okay, which will look pretty complicated, okay, but the main point is not to look at the exact details of the expressions, okay, but I nevertheless wanted to show you the expression just to convince you that those expressions exist, right. They are concrete expressions that you can write down and you can calculate. So here are the expressions for the coefficients A mu nu, B mu nu, and C mu nu. Okay. The only thing that I want to point out here is that you can see that the only dependence that it has, the only things that appear on the right hand side, okay, are of course this distance. the universal constants, the Newton's constant and the speed of light, okay, and the momenta of the ingoing and outgoing particles, okay, and n here is a 4 vector that is defined here, okay. The first component of n by definition is 1, and then this is what I had called n hat earlier, that gives the direction in which the detector is placed, okay. And you can see that everything that appears in this formulae is determined by these quantities, right. There is nowhere in this formulae that there is any ambiguity, okay. You don't need to know what kind of interactions took place during the collision, okay. It does not even depend on what kind of angular momentum the particles are carrying as they are coming in and going out. Here are the expressions for the f and g, okay. They are more complicated than what you saw earlier, but nevertheless they depend on exactly the same set of variables, right. There is no additional variable that appears in these expressions. So now I will discuss some aspects of these results. So you have these features, mu nu for large positive u, that means late time, has this form, and mu nu at large early time has this form. Mu nu here is what is called a memory term, okay. It is a somewhat strange object, because you see what it says is that you start with mu nu being 0, right. That means no gravitational field at the beginning, right. Then the wave comes and hits you, okay. Then there is some oscillation, right, h mu nu changes, the wave passes, okay. After the wave has passed completely, okay, the gravitational field does not return to 0, okay, but returns to a constant, okay, which means that the detector that if you set up the detector in certain way, right, the gravitational wave passes, the detector starts detecting, right. At the end of the process, the detector does not return to its original position, right, because of the fact that the gravitational field at the end has changed from 0 to mu nu. This is what is called a memory term, okay, which is a permanent change in the state of the detector after the passage of the gravitational wave. Okay. This is not a new observation, this in fact had been known for many years, since the 70s, okay, but this was revived in more recent developments by Strominger, Zibodov and others, okay, where they made connection between memory effects and soft theorem, right, and part of which I will describe in later. These terms are what are called tail terms, okay. These were in fact discussed, these universal formula for these were found only after we analyze the result through soft theorems, right. These are not known in this universal form to the earlier before this, right. So these are genuinely new results that come out of analysis of the soft theorem that I will be describing later. Okay. What was observed earlier was special cases of these, right. In specific scattering processes, people did find that there are coefficients of this kind. Now, if you look at the expressions for these coefficients over here, okay, these are the ones that come at late time, okay. A mu nu is a constant term, b mu nu is a coefficient of 1 over u, and this is a coefficient of 1 over u square log u. Okay. This depends on both incoming and outgoing momenta, okay. And in the sum over final state particles, right, which is A and B, let me show you that one of the formula, right. See in the expression for f mu nu, the momenta without primes are the final state momenta, these are the ones that come at the initial state, right. So f mu nu depends on the final state momenta, right. So here you are supposed to sum over all final state particles. Now this all final state particles will mean also the gravitational radiation, right, because gravitational radiation you can also regard as a flux of massless particles that is coming out of the detector, right. So you have to include the contribution from gravitational radiation in these, in the expressions for these, and this makes it hard to calculate these objects, right, because this is saying that okay, you have some incoming particles, some outgoing particles, right. In terms of this you can calculate these coefficients, but the outgoing particles involve gravitational waves, right. So unless you actually calculate those gravitational waves, you cannot calculate what these coefficients are, and this is indeed true for a mu nu, okay, and this again has been known for a while. This is what is called a nonlinear memory term. However, there is some miraculous cancellations, okay, which we still don't understand why this happens, okay, but I'll explain what these cancellations are. Okay. Due to these cancellations in this B mu nu and F mu nu coefficients, okay, the contribution from the massless final states can be expressed in terms of the massive states. Okay. In other words, if you look at this expression for F mu nu, okay, in this sum over final states, right, you are allowed to drop all massless state contribution, right, which includes gravitational waves. Right. So just remove from this sum, restrict the final state sum only to the ones that carry that correspond to massive final state particles. Okay. Now these of course you will make an error, okay, but it seems that there is a simple way to compensate for this error, and that is this. Okay. Then you drop massless particle or radiation contribution in the final state, and you just add a term like this, okay, where Pi is the total incoming momentum and Pf is the total outgoing momentum, but carried only by the massive particles. Right. So Pi and Pf are not the same in general, right, because total momentum is conserved, but the momentum carried by the massive particles is not conserved. Okay. So you just add this term and drop all final state particles and you get the same result. Okay. Similarly, in F mu nu we can drop massless particle or radiation contribution in the sum of a final state and just add another term of this kind, okay, where Pi again is the total incoming momentum, Pf is the total final momentum. Okay. Now what I want to emphasize here, okay, is that these are not new formulae. Okay. These are just rewriting of the original formulae, right. So even if you didn't know anything about how this formulae came, right, if I tell you, if I give you this formula, right, you can check explicitly just by doing some algebra that you can drop all massless contributions in the final state and add these terms and you get exactly the same result. Okay. So we don't have a deeper understanding of why this is true, right. This just happens to be the case. We discovered it just by examining the final formula, okay. But we believe that there must be some deeper reason why this happens.
I have a question.
Yes.
Are you saying that the massless terms all sum up to this?
Yes.
Okay.
Exactly. Right. Just drop all the massless contribution in the final state and they sum up to this. That's exactly the statement. Okay. If there are other questions, maybe I can answer at this stage, because now I am going to give the derivation of some of these results.
Excuse me, sir.
Yes.
Actually, like we are talking about the particles in the sense this heavy particles or the particles which are going to collide and
Yes.
giving that gravitational waves, right?
Yes. Particles could be planets also, right?
Yeah.
Or
Then
black
how,
holes.
like what do you mean by that massless term actually? Like which is massless here?
Yeah. So massless is that, imagine the two black holes collide. In that process, it will form a third black hole and also a lot of gravitational radiation, right? They carry a lot of energy. So the gravitational radiation is what I am treating as massless particles going out, right? Because gravitation, what matters is the total energy flux, right? Total energy and momentum flux. Whether they are carried by particles or waves doesn't really matter, right? So in this, when you write sum over momenta, right, it could also involve sum over momenta carried by waves. Okay, if electromagnetic waves are emitted, they also have to be counted in this process. Yes. Yes. Yes.
And we are observing here.
Yes.
So are you assuming in between there is no dust or all other things which are there which are going to absorb some of the energies?
Yeah, so those also of course have to be taken into account separately, right? If there are additional effects. So what I am describing here is just collision, right? Emission of gravitational waves, and we assume that the gravitational waves come to us and what we
So
observe
this is the
them.
formula at that close to that location where the event is taking place.
Yeah, this is a
What you
formula far
observe-
away, assuming there is nothing in between, right? If there is something in between, that gives you additional corrections
They
that you
are
have to
there,
compute.
they are there. in
Exactly.
between, and
So you have to
dust is-
compute the corrections for
be
those.
reduced.
Yeah, but those are really not very big, right? Because when you take black hole merger, for example, right, what you match is the numerical simulation that you get directly from black hole merger, right? There, of course, also the gravitational wave comes to all the galaxies and stars, but those effects are very small, typically.
Okay.
So a small clarification.
Yes.
So you're talking about the classical gravitational
Yes.
radiation. I
Yes.
suppose. When you say particles in the final state, what do you mean?
Particles could be black holes, stars, right?
Okay. But the gravitational wave itself not thought of as particles.
Gravitational wave, the emitted gravitational wave, right?
Yeah.
We can think of as particles or waves. As I said, it doesn't matter. This sum over p that I described, it could be carried by particles or waves, right? They contribute equally. So you can think of gravitational waves as carrying momentum and energy as waves, or you just think of as a bunch of gravitons which are carrying the energy away, right? The
Okay.
formula is the same.
When you say particles, I can think of a wave packet kind of thing.
Yes, you can think of the wave packets,
Okay.
right? Or just big waves also, yeah.
All right.
Exactly.
Sir,
Yes.
one more basic question actually.
Yes.
We said gravitational wave is 1 by r, right?
Yes.
So should I say it's like more, it is more, it's more than electrostatic or any other r square terms?
Yeah, the 1 over r of course is more than 1 over r square, but electromagnetic wave also falls off as 1 over r, right? So the waves always fall off as 1 over r, right? It's common between gravitational waves and electromagnetic waves, right? Whereas the static fields fall off as 1 over r square or faster at large r. Okay, so with this then I'll proceed. Oh, maybe I should have said some things also, that this formula that I described, right, we are assuming that the incoming and outgoing particles do not carry charge. Okay. If they do carry charge, then there are additional terms in the formula, but those are also known. I just didn't write them down because it will just make the formula even more complicated. I started the talk by describing explosion, but explosion of course can be regarded as a special case of scattering when the initial state has just one object, right? One object blowing up into many objects, right? That's also part of this general idea of collision. In this case, the early time coefficients C mu nu and G mu nu will vanish. It just follows from the formula, and E mu nu will take this form, right? Only the late time behavior is important. And finally, for binary black hole merger, right, the final state has just one massive object, right, and many massless objects. Okay, again, these massless objects you can think of as lot of gravitons going out of the system, or just gravitational waves carrying away energy. Okay, but either way, you can regard them as massless particles, okay, which are carrying away the energy. And so in this case, one can use this formula that I described, right, use these replacement formulae, okay, and one can show that the final state results exactly cancel. So 1 over u and 1 over u log u over u squared coefficient vanishes even in the final state, right. So the only thing that remains there is the memory. Okay, we can ask how big are these effects, okay, is it ever possible to observe such things? So this you can easily calculate because of the formula, so you can put in some numbers. So if you have a core collapse supernova in our galaxy, right, this could produce a strain of order 10 to the minus 22 after about 1 second, okay, if we choose the parameters favorably. Okay. And just to put things in perspective, I mean, we expect that in our galaxy, okay, on the average there is maybe one supernova in 100 or 50 years, right. So you have to wait for 50 years to see such a thing. The bullet cluster that I started with, right, it actually produces a strain that is much stronger of order 10 to the minus 14. Okay. Oh, maybe I should have said that the LIGO can observe a strain of order 10 to the minus 21 today, right, and it will improve in the future. So it's on the borderline. This is much bigger than 10 to the minus 21, okay, but unfortunately it varies over a time scale of order 100 million years, right. So it's not really possible to observe it today, right, because you cannot wait for 100 million years in a gravitational wave detector to see this. But the strain in different parts of the universe is different because of the bullet cluster, and this may have some cosmological consequences that may be seen sometime in the future. Okay, so now I am going to go into the derivation, and so from now on we are going to set the speed of light equal to 1. Okay, you can always put them back using dimensional analysis, but it's just that in order to avoid cluttering the formulae, I'll set the speed of light equal to 1. So let me describe briefly how we derive it from soft graviton theorem. And as I said, soft graviton theorem is a resulting quantum theory of gravity. Right? The results that I have been describing are purely classical results. Okay? So one might ask, how can a quantum result in gravity have anything to do with classical results? And this is the part that I will try to explain now. So in quantum theory of fields, okay, which is what is normally used for things like quantum gravity, the scattering amplitude gives the probability amplitude for transition from one state to another. The absolute value square of the scattering amplitude is the actual probability. This is a transition probability from one state to another. Now let us suppose that we know the scattering amplitude A for transition from some incoming state P to some outgoing state Q. Here P and Q could contain set of particles, right, and in general they can be defined. So imagine that the P consists of a set of particles that are coming in, Q consists of a set of particles that are going out, okay, and we want to calculate the probability amplitude for this process. Right. A set of particles carrying certain momentum coming in and a set of other set of particles carrying certain other momentum going out. Now this is in general difficult to calculate, this A, because this will depend on the details of the interaction, details of what kind of forces operate between these incoming and outgoing particles. What soft graviton theorem gives us is that this gives us the transition probability amplitude for a different process, okay, which is the process of P going to Q plus some low energy gravitons. Okay. Now this word graviton may not be familiar to everybody, so this graviton is essentially what you get as a massless particle by quantizing gravity, right, just like photon is a massless particle that you get by quantizing electromagnetic force. Right. So graviton is a massless particle of that kind. Okay. So imagine that you want to calculate the transition probability for P going to Q plus some low energy gravitons. Okay. The soft graviton theorem tells us how to compute this, okay, in terms of the transition amplitude for P going to Q. Right. So while P going to Q is a very complicated object to calculate, this is simpler once you know P going to Q. Okay. So this is the content of the soft graviton theorem. It relates one process to another, even though both may have complicated expressions. So this was a quantum process, right? A set of particles coming in, a set of particles going out. Okay. Now we want to understand how to take the classical limit, okay. And probably it's familiar to most of you that the classical limit, the classical physics applies to big objects. Right? So we take the classical limit by taking the incoming and outgoing object, the states in P and Q, the particles which are coming in and particles which are going out, to be very massive objects, okay, very energetic objects, coming in, going out. So then we calculate the transition probability for P going to Q plus m low energy gravitons. Each of these we take to carry some energy, h bar omega, h bar is the Planck's constant, and momentum, which is h bar omega times the direction n hat, this is a unit vector. And what one finds as a consequence of soft theorem, that this transition amplitude, the dependence on m has a very simple form. It takes the form of r times s to the m over m factorial. Okay. R is complicated to calculate, it depends on the details of the scattering process. Okay. S on the other hand is what is called a soft factor. This depends only on the properties of the incoming and outgoing objects, and furthermore it is large in the classical limit. Okay. So while we do not know how to compute R without knowing the details of the theory, we do know how to compute S. And so at least part of the formula we know, right, and this m factorial is the result of both statistics, right. You have to symmetrize in the external particles. If there are m external particles, right, they are all indistinguishable, so we account for that by dividing by this factorial m. So imagine that you have such a process, right. Quantum mechanics tells you that all m's are allowed, right. There is no point in asking how many gravitons are emitted, right, because quantum mechanics gives you the probability for different processes. There may be 0 gravitons emitted, right, whose probability will be R. There may be 1 graviton emitted whose probability will be R times S, 2 gravitons, R times S square over 2, and so on. But now we notice that this quantity R S to the m over m factorial, okay, as a function of m has a sharp maximum at m equal to S for large S. Okay. Now of course m is an integer, S is not, so you think of m as the integer that is closest to S. Okay. That is where the probability is maximum. Okay. Furthermore, this maximum is sharp, right, which means that if you look at the probability at different values of m, right, at certain value of m the probability peaks and then it falls off very sharply on the as you go away from the peak. Okay. This means that even though quantum mechanics allows the production of any number of gravitons, right, 0, 1, 2, 3, etc., okay, the probability actually peaks around a certain value, okay, and that value is what we normally identify as a classical number, right, because it is saying that in the classical limit, right, the probability is sharpened, right, and so then from the classical perspective, if you have a collision like this, only a certain number of gravitons are emitted, right. Most of the time the number of gravitons emitted is that, the S, right. Once in a while it is a little less than S, once in a while it is a little larger than S, but most of the time it is S. Okay. This is what we call the classical number. This is the way the classical limit emerges from quantum mechanics. Okay. And the energy that each of these gravitons carry is S times h bar omega. Right. So the total energy carried by these gravitons is S times h bar omega, because each of them carry energy h bar omega, right, and momentum h bar omega in hand. So you conclude that the classical flux of energy carried by gravitational wave of frequency omega is given by this, right. S is something that is easy to compute. This is given in terms of the incoming and outgoing momentum. And now once you know the energy flux, right, you can translate this to time Fourier transform of the gravitational wave form h mu nu, okay, expressed as a function of omega, the frequency, okay, and then you can take the inverse Fourier transform to get the late and early time profile, and that is what leads to the results that I quoted earlier. Okay, then you compute S is known, so S is related to the Fourier transform of the gravitational wave form, okay, and then you Fourier transform back to get the h mu nu itself. Now this classical, soft theorem analysis has some drawbacks in 4 dimensions, what are 4 space time dimensions. That is what we are interested in. Okay. The first drawback is that the usual soft factor is infrared divergent, okay, and we need to regulate the infrared divergence by some physical principles. Okay. There are known physical principles that do regulate the infrared divergence, okay, but you have to put them in explicitly. Second drawback is that because the analysis proceeds by computation of the energy flux in different frequencies, it is insensitive to the frequency dependent phase of the waveform. Okay. In other words, the energy flux is actually related to the absolute value square of the Fourier transform of h mu nu. Okay. So that determines the Fourier transform of h mu nu up to a phase that can depend on the frequency omega. Okay. And we need that phase to find the detailed form of h mu nu. Okay. So that phase has to be determined by separate computation. Okay. Nevertheless, both can be done, okay, and that is what leads to the results that I described. It is also possible to get the result by direct classical analysis, and that is what I am going to describe in the next few minutes. Okay. But so this does not have these shortcomings, but it is certainly much more complicated. Okay. And the results that I described are first obtained using the quantum soft theorem, okay, and then a more explicit classical derivation was found, right, because after all these are classical results, right. So it better be that there is a classical way to derive it, right. It is like quantum mechanics is an easier route to get to the result, okay, but a classical result should be derivable from classical physics. Okay. So let me describe the direct classical derivation and then I will stop. So what is the goal? Okay. We want to find the gravitational waveform, the h mu nu or equivalently e mu nu, that is generated during the collision process. Okay. So we try to start solving classical equations, right, and the classical equation that determines the gravitational field is Einstein's equation, right. So, you write down Einstein's equation, okay, and try to manipulate it to see how you can solve it. Now, it turns out that in the redundant gauge, okay, there is some technical words, in some particular gauge the Einstein's equation that determines C mu nu can be written in this form, okay, where box is a standard Laplacian in flat space time which is given here. Now, this looks too simple, right, there is no nonlinearity that you see in this equation, okay, and that is because everything has been hidden inside T mu nu. Okay. So, T mu nu on the right hand side, that includes the usual energy momentum tensor, the source of gravity which is the particles that are moving in, okay, but because gravity is nonlinear it acts as its own source, okay. Those are captured in the nonlinear terms in the Einstein's equation, okay. So, all of those you have hidden inside T mu nu, right. So, we no expressions for T mu nu in terms of E mu nu, but it does depend on E mu nu, okay. So, the right hand side, right, even though it looks simple, right, the T mu nu actually has a non-trivial dependence on E itself, right. So, this equation, this is a nonlinear equation, right, with the nonlinearity is hidden inside T mu nu. And furthermore, we do not even know, we may not even know what the full structure of T mu nu is, right, because we may not even know what all the interactions are involved, right. If there are nuclear forces involved, right, then those will also go into the expressions for T mu nu, and we do not a priori know what kind of forces there may be. Anyway, so let us proceed. Okay. So, we will now define the time Fourier transform. Okay. We take the Fourier transform in the time variable, okay, and this is just an overall phase that I have added, right, but this is the important part. And now ask that the kind of terms that we are looking for, right, E mu nu going to a constant or 1 over u or 1 over u squared log u, right. U is basically T minus mod x in this picture, okay. That what do they translate to in terms of the Fourier transform variable E tilde, and here are the results that you can easily verify by taking Fourier transform, that if you take E mu nu going to a constant for large positive or negative u, okay, these correspond to the Fourier transform E tilde mu nu as a omega plus minus I epsilon inverse, right. This plus minus I epsilon basically means that if it goes to a constant for large u, then it is omega plus I epsilon inverse, where epsilon is a small positive quantity, and if it goes to large negative u, right, that is our far past, then the Fourier transform is omega minus I epsilon inverse. Similarly, if E mu nu goes as 1 over u for large positive or negative u, these correspond to the Fourier transform being log of omega plus minus I epsilon for small omega, and if this goes as log u over u square for large plus minus u, then these will correspond to E tilde mu nu being omega log omega plus minus I epsilon square for small omega. Now, the key feature that will be important in our analysis is that these terms that you see here, okay, are all non-analytic at omega equal to 0. Okay. Now, what do you mean by non-analytic, right? Non-analytic does not necessarily mean that this is a divergent, right. This diverges at omega equal to 0, right. This also diverges at omega equal to 0 as you take epsilon goes to 0 limit, right. But this one does not, right. Omega log omega square actually goes to 0 as omega goes to 0. Okay. So, non-analytic does not necessarily mean that it should diverge, okay, but that if we take sufficient number of derivatives of these with respect to omega, then set omega equal to 0, then it will diverge. Okay. Omega square, for example, right, does not have that property. You take derivative of omega square, after 2 derivatives you get 0, right. It never diverges at omega equal to 0, but omega log omega square, right, if you take the first derivative with respect to omega, then you can get rid of this omega and then it will diverge at omega equal to 0, right. That is what I mean by non-analytic, right, and this is the property that will be important for us. Okay, so you have to solve this equation, right, and now I will formally solve this, okay, by retarded Green's function, right, the standard method that one uses for even electromagnetism. Okay. Now, again when I say solve, right, it is not a solution because this gr, the t here on this side involves c, right. So, it is in no way it is giving a expression for E because this depends on E, right. So, it is an equation that involves E, right, except that instead of a differential equation, now you have an integral equation. And one can now take the time Fourier transform, and using the explicit expression for the retarded Green's function in 4 space-time dimensions, one can show that for large x, large distance, the time Fourier transform has this structure, right. It is the full Fourier transform of t multiplied by this 2g over x, right. This is just a simple mathematical step to go from here to here, right. Just take the Fourier transform of this and then go to large x limit. Now, here is the key point, right, that allows us to handle this problem. So, we are looking at this equation over here, and you have to evaluate this integral on the right hand side, and this integral runs over space and time, the whole space time region, right, all space and all time. Now, we are going to divide the integration region over y into 2 parts. One we call the scattering region. This is a region of large size around y equal to 0, that means it is a region of large size around the space time point where the scattering is taking place, right. If the scattering was taking place at t equal to 0, x equal to 0, right, we take a very large region, right, around x equal to 0, a very large time interval around t equal to 0, that is what we call the scattering region S. And then the asymptotic region is a complement of S, everything else. And the point is that if we are looking for non-analytic terms in E tilde mu nu, and those are the ones that we need for studying the part of the waveform that we are interested in, the constant part 1 over u part and the 1 over u square log u part. The non-analytic terms cannot come from integral of a finite quantity over a finite region. So, you look at this expression over here, right. We know that if you take sufficient number of derivatives with respect to omega, it should diverge, right, that is the non-analyticity. You start taking derivative with respect to omega, right. What do you get here? The omega dependence is through k, right. So, you will start getting factors of y in the, it will pull down factors of y, right. But however many factors of y you pull down, if you are integrating over a finite region, it is also always a finite answer, right. Then we y to the 100, but y is integrated over a finite region, so that is a finite answer. So, these cannot give non-analytic terms. The non-analytic terms have to come from the region outside the scattering region. So, this is what I have said here, and in this scattering region only long range forces are important. Furthermore, in this region, right, we can assume that E mu nu is small because you have the scattering has happened and you have gone far away from the scattering region. So, the gravitational field is falling off as a 1 over r. Right. So, far away from the scattering region, the gravitational field is small. Okay. So, we can, even though you have nonlinear terms, they are under control because you can expand in parts of E mu nu and try to solve the equations iteratively. Okay. So, the result for T mu nu simplifies, okay, and the equations can be solved iteratively, and that is what gives the result that I quoted earlier. Okay. So, in fact, the first iteration gives you the memory term, the second iteration gives you the 1 over u term, and the third iteration gives you the 1 over u square log u term, right. So, that is the way we solve these equations. So, in this slide I have summarized all the equations that you have to solve, right. Basically, the only term that you do not see is the expression for the th, which is a bit complicated, right, but it is a straightforward process to write down the expression for th. Right. So, we start with E mu nu equal to 0, right, and trajectories being just straight line trajectories, right, because in the absence of gravitational field particles move along straight lines. Okay. So, you put them in here, right, the particles are moving along straight lines. Using that you calculate Tx, right, because E mu nu is 0, Th is 0 in the first iteration. So, you just have to solve for box C equal to minus 8 pi g Tx, okay. That gives you the memory term. Then you take that E, right, put it back here, right, these are the Christoffel symbols. Okay. You have to calculate the gammas in terms of the E's. So, now the trajectories get modified, right. The modified trajectory you put in here, you solve for Tx. Now, you also have Th because E mu nu is non-zero, right. So, you evaluate the right hand side and then again solve this, right. That is the first iteration, that gives a 1 over u piece, and then in the next iteration you will get 1 over u square log u, right. So, that is the way these equations are solved. And you see that because we can exclude the scattering region from this analysis, right, all the details of the interaction are unimportant, right. Only long range forces operate outside the scattering region, right, and that's gravity and electromagnetism. Now let me just end by saying, describing some possible generalizations. So there is reason to believe that the coefficient of the 1 over u to the n plus 1 log u to the n, these terms may also have universal properties, namely that they depend only on the momentum of the particles. Right? This has been argued by both Biswajit and then later by these people. So the question is, can we compute them? So in this case we can no longer rely on soft theorem, right. Soft theorem was very useful to get the answer, but we cannot rely on it because soft theorem extends only up to the first subleading order. But direct classical analysis may be possible. What I described earlier, right, we can just repeat this one more time, right, iterate it one more time to get the next order term, right, and you can repeat it once more to get the next order term. So this may be possible, we do not know yet, right, this is still work in progress. Now you may ask, what is the ultimate goal? Okay, one of the goals will be to use these results in reverse, right, because you see if we knew the coefficient of all of these terms, right, this is infinite set of data, right, involving external incoming and outgoing momentum. And the idea is that by measuring the gravitational waveform in a detector, we can measure the coefficient of these terms, and then because these coefficients are known functions, if they are known functions of the incoming and outgoing momentum, then knowing these coefficients we can try to reconstruct the initial and final states of the event that led to the production of the gravitational wave, because we do not know what is happening, right, we are only seeing the gravitational wave coming in, okay. And the question is, knowing the by observing the gravitational waves that are coming in, okay, to what extent can you reconstruct the event that took place, right, at least can we say what went in and what went out during the scattering process that produced a particular gravitational wave, right. This is one of the hopes that of this program, that we may be able to get it by studying the coefficients of these terms. As I said, we do not know if this is true or not, but there is an analog of this problem for electromagnetic radiation, okay, and that problem has been solved completely now, right, and we do know that the coefficient of the 1 over u to the n plus 1, 1 over u to the n log u to the n plus 1, sorry, 1 over u to the n plus 1 log u to the n, right, those coefficients can all be computed and they are universal, right, they depend only on the mass and charge of the external particles. So we know the result for general m to n scattering, right, but it is a bit complicated to write down, but for 2 to 2 scattering there is a closed form that you can write down, and here it is, right, this is given in terms of the time Fourier transform of the electromagnetic field this time, okay. And again, if you examine this formula carefully, you will see that all that goes in are the momenta and the charges of the incoming and outgoing particles, okay, and you know the coefficient of arbitrary omega to the k minus 1 log omega to the k terms. So these are my final slide, okay. There are related developments, okay. Some of these results have also now been derived from what is called the asymptotic symmetry analysis, the analog of BMS symmetry and its generalizations. As we saw, the coefficients of the u inverse and 1 over u square log u, these terms are independent of the spins of the external particles. Even if the external particles were spinning, the result does not change, but the coefficient of the 1 over u square term in fact is spin dependent, and the corresponding results are semi-universal, and they can also be derived both from soft theorem and by direct classical analysis, right. So and this was done by Ghosh and Sahu. I think Ghosh was a student at IMSC at the time that he wrote this paper. And finally, I should just say that there are also quantum versions of the soft theorem that involve corrections to the amplitudes. There are corrections to the quantum amplitudes of this form, and these have also been studied in various papers. So I think I will stop here. Thank you. Thank you.
Any questions? I know some of you have already asked questions during his lecture, but do you have anything now? Any questions?
So you said that gravity has non-linear effects. And
Yes.
you also mentioned that like it acts on its own source.
Yes.
So what does it mean by that? Like gravity acting on its own source?
That if you have a gravitational field is produced by energy, right? Energy is a source, and the gravitational waves carry energy, right? So they produce their own gravitational field. Right? That's what one means by saying that the gravity acts as its own source, right? Because gravitational field itself carries energy, right? It produces a gravitational field.
Thank you, sir.
Right? So mathematically, when you write down the field equations, right? In electromagnetic field equation, there is a in Maxwell's equation, for example, on the left hand side you have a linear term in the Maxwell field, right? D mu F mu nu. On the right hand side you have a source term, right? The source term doesn't depend on the electric or magnetic field, right? That depends on the particles. For gravity, the source term itself depends also on the fields, right? As square or cube of the field. So that's the difference.
In page number 25, if you can go.
Page number 25. Yeah.
Just before, actually, I think. No. Maybe before.
Before that, or after, you tell me the subject, the kind of subject.
It is you have this exponential of S.
Okay, yeah, this one. Maybe.
25.
This is
It's 22. I can't read that.
22.
Okay,
yeah.
this is the amplitude or scattering?
This one? No, this
probability?
one is the way I have written it. This is a probability. You have already taken mod
And you
square.
mentioned that it has infrared singularity.
Okay, infrared singularity, I'll come there. Yeah, that is here. Here. This is infrared diameter.
And this problem is happening because you have soft emissions and things like that, right? This
Yeah,
infrared diversity.
yeah.
But in it's a QED or QCD, if you include virtual corrections, these things go away. You can define as a Sudakov factor or something like that.
Yeah.
This is possible here also,
Yeah, see here the point is there is a natural infrared cutoff that is already there, right? Because the infrared cutoff here comes from two sources. One is that the particles are going out, right? So at any given time the particles have gone a finite distance, right? So that provides a natural infrared cutoff because they cannot affect their motion cannot be affected by the gravitational field outside that, right? So that gives you one kind of infrared cutoff. The other one comes because the detector is placed at a finite distance, right? So what is happening beyond the detector is irrelevant, right? So these are the two infrared cutoffs that you have to put in, and that automatically solves.
Do you have any similar analogy in the electrodynamics, classical electrodynamics, where you can also have similar singularity?
Yeah, I think you can probably, the energy resolution that the detector has, I think can be related. There you say the detector has certain energy resolution, right?
Yes.
And that can be related to how far the detector is. Because imagine the detector is placed at a distance r away, right? It cannot possibly observe energies with an accuracy that is less than 1 over r, right? So I think it's related to that physics.
But there also they subtract this virtual part and things like that. Actually.
Yeah, see the virtual part is already included.
In block not sick, without virtual part, even with resolution, you will not get finite answer. No?
Yeah, but that is actually automatic here, right?
Okay.
Because this one is a full quantum amplitude.
Okay.
I mean, which includes the virtual part, right? Okay. What I am writing here is the full quantum. The S involves quantum corrections already.
Okay.
Yeah, so that certainly has been included in this.
Okay.
Right?
Thank you.
But after that, you need this infrared cutoff, right? And that is the analog of having the finite detector resolution in QED.
Okay. Thank you.
Sir, in the expression for E mu nu that you had shown in the results, the memory term is only in the case of large positive view.
Yes.
Is that because for the gravitational wave has not reached the detector for the negative?
Yeah. So this is a matter of convention, right? Because a constant E mu nu, right, can be removed by coordinate change, right? So I have chosen my coordinates in such a way that before the gravitational wave has reached the detector, I have declared the gravitational field to be 0. Right? Otherwise, I could have chosen another coordinate system in which it is non-zero, right? But that's not something you can observe, right? It's a change in E mu nu that is relevant, right? So the memory term, really is a difference between the constant coefficient in the far future and the constant coefficient in the far past.
I have a
a generic question.
Yes.
So you said that the final goal or the big goal of the program is to reverse engineer and figure out what is the initial state and what is the final state.
Yes.
So by that you mean like what kind of
Scattering
physical
took
objects that interacted and then what you produced.
Exactly.
So is there any hope that, let's say, like you want to know the quantum effect? Let's say the gravitational wave is coming from like some process that happened during Big Bang. So is it at least theoretically possible to expect some sort of miracle like that? So you learn something about quantum gravity from gravitational
It is
wave.
possible in principle, right? That way you can say, okay, even if you find, for example, in the CMB spectrum, right? If you find a B mode polarization, right? We will know that that those are produced by gravitational fluctuation, right? So that's an indirect effect of quantum gravity, right? That we can actually see today in the classical observation. Right? So such things are certainly possible, right? But what I was describing here is purely classical process, right? But it is possible in principle that the tiny quantum effects in the early universe could get amplified, and today it may appear as a big classical effect.
But those are not scattering cases.
Those are not scattering cases, yeah. Those are not scattering cases. Yeah, exactly.
Sir, how? So in the end, you did this thing where like you had, I mean, like a 2 to 2 QED scattering, and then in that, like you assume that some energy omega is like taken away by gravitons, right?
So here it was a purely QED process. Let me.
Yeah.
So
here
there is
it's
no
a purely QED process, and omega is the energy that is
of the photon.
Oh, not of any graviton.
It's in now everything is QED. Right?
Okay.
So
Okay.
this is analog of. So what I was showing is that the analog of the problem for QED can be solved.
Okay, so the waves that you are like measuring later on are also like photons only, not gravitational.
So in this slide,
okay,
everything is electromagnetic.
So here you are just assuming that there's some electromagnetic interaction and like it's releasing out photons, and if I were to measure it, okay.
Exactly.
Okay.
But that interaction that is taking place could involve nuclear interactions or more other interactions, right? It doesn't matter as long as the long range forces are only electromagnetic, right? This formula is valid.
Yeah.
Okay. So that's the universality. So that's the analogy with what we saw earlier, that it's completely universal. It doesn't depend on what kind of forces acted during the scattering process, right? But only what the long range forces are.
Okay. And like in this, like the particles which are going for this, and not for this case, but like when you're doing the analysis, you're saying that like you have P and Q momenta and like they are the gravitons are taking away, but in the classical case, like the P and Qs involve the gravitons as well.
Yes. But here things are simpler because electromagnetic waves are not sources of electromagnetic waves.
Here as in like when you do the analysis for that R S power K by, in that case you're not, you're taking P and Q to, Q doesn't include the momentum of the gravitons themselves.
No, it could, yeah, because the soft graviton theorem, right, what it says is there may be hard gravitons in this process, right, which are carrying a finite energy. Those are also included in Q.
Okay.
Right. So so in terms of those, you calculate the soft graviton emission, right? Okay. The low frequency graviton emission.
Yeah. Hello, Professor. Professor, you mentioned that there are changes in the LIGA, in the instrument itself.
LIGO, yeah.
Yeah, LIGO instrument. Could you elaborate what you mean by the change in the state, and what does it mean to? Does it mean that after a short wave has passed, practically does the instrument have to be reset, or what do you mean by the state? And the second question is that if there's a long duration traveling wave, is that affecting all the detectors and changing its configuration somehow?
Okay. No, long duration is okay. Let me ask the first question. Answer the first question. So imagine that we have, so gravitational waves are detected by some interference effects, right? You have two arms of a detector, right? And you set up the system so that there is destructive interference. It's an interferometer, and your initial configuration that there is destructive interference, right? So there is no signal. Okay. As the gravitational wave passes, the detector, the relative lengths change, right? And you start seeing a signal. Okay. What this is saying is that after the signal has gone, right, it doesn't come back to destructive interference form, right? Because the relative lengths of the arms are still different from what it was earlier. Right? So you have to reset the instrument. If you want to set it to destructive interference form, you reset the instrument, and LIGO has an inbuilt mechanism to do that. Right? It brings back the instrument to the destructive form after the wave has passed. But there will be space-based experiments, right? The LISA. There is no restoring force, right? Once the detectors are moved, you have to live with that, right? So it goes into the new state, and then you wait for the next signal, right? To see how the signal change, how things change. Sorry, and the second question, maybe can you repeat again what you said about the?
Long duration process. If there's a long duration a gravitational wave, like you are mentioning some non-observable thing because the duration is in the order of years.
Okay, yeah.
So that's going to be affecting all the detectors in a similar way.
Yeah, that is affecting all the detectors, but what we normally observe in a detector is a change, right? So if there is some change that is taking place over long years, right, it doesn't really matter in practical terms, because you are for the short duration gravitational waves, right, you are measuring the change from what happened before the wave and what happened after the wave. Right? Long duration ones are superimposed things on that, right, but that doesn't affect the detector during that short change.
Okay, I have a question.
Yes.
So initially you started out with this computation and of these A mu nu, B mu nu, these things, and there was some cancellation which was helpful.
Yes.
So are these tree level calculations? Can loop level?
No, these are not tree level. These are exact, right? So that's the beauty of soft theorem, right? No approximation is made here. Right? As long as you say that the only approximation is the expansion in u, right? You are calculating the coefficient of the constant term 1 over u term and 1 over u square log u term. Okay. Other than that, right, it's an exact result. You don't make any tree or loop approximation, right? It's completely general.
Okay, and one more thing is you mentioned at the end that if one knows these coefficients, one can talk about what goes into the initial states.
Yeah, in principle, right? We don't know, since we don't have the formula. See, the point is that for this to happen, right, we have to make sure that the coefficients of these terms are all independent functions of the momenta, right? Imagine that all of these depend on the same combination of momenta, right? Then of course it will not help in reconstructing the momenta, right? Assuming that these are independent functions, the hope is that you can reconstruct the what went in and what went out. But since we don't have the formula, right, we don't know if that is true or not.
Okay, and a very nice question, like for the bullet cluster thing, does it also say something about dark matter, or is some assumption made about
for
matter?
what
for
thing?
the bullet cluster estimate.
For bullet cluster, yeah. So bullet cluster, in fact, is one of the evidence for dark matter, quoted as one of the evidence for dark matter, because what one observes in the bullet cluster is that the visible matter, okay, that it's like two superclusters which are passing through each other. Right. The visible matter, because they have higher interaction, they collide, there is friction. Right. So what happens is that the visible matter proceeds much slower than the dark matter, because dark matter has no friction, right, or very little friction, so they go out. So what one finds is in the bullet cluster is that the two merging galaxies are much closer to each other, the visible part, and the dark matter part, right, which is seen gravitationally, is like bulge which goes out, right. And that's taken as the evidence for dark matter. There is two kind of object, right? The baryonic matter, which is which has high friction, they don't move that fast past each other, and the dark matter which move faster past each other.
No, my question was, how does that input also go into the calculations? Like, is it by the mass of the particles?
Yeah. So in the calculation, you can, to first approximation, you can take the mass of the dark matter as the main contribution, because dark matter density is much higher than the matter density. Right? Otherwise, you think of it as the incoming object as a set of two objects, right? One consists of visible matter and one dark matter, and similarly the outgoing object as two different objects, one consisting of ordinary matter and one consisting of dark matter, right? Because their momenta will be different. But most of the contribution here will come from dark matter, because dark matter is the major constituent of these clusters.
Thank you.
Yeah, sorry.
I had a small question. So in the soft graviton theorem, we
Yes.
are kind of breaking the contributions of gravitons into soft gravitons, and as you mentioned earlier, there can also be hard gravitons which are included in the
Yes.
Q part. So my question is, on what energy scale basis are we distinguishing the gravitons into hard and soft?
Yeah. Okay. So you don't really have to do that, because what you can show is that in this sum, you can ask, okay, can you include the soft contribution, right? So you can do the soft contribution include the soft contribution in this sum, and what you find is that those contributions, right, at this level do not affect the result at the 1 over u and 1 over u square log u level. Right? They will start affecting at higher order, right? Maybe 1 over u square terms may be affected by those, right? The effect of soft graviton on themselves, right? Or 1 over u cube will be affected by those. But these terms, 1 over u and 1 over u square log u, you can explicitly check that they are insensitive to where you put the cutoff.
Thank you.
Yeah, this is a follow-up of the previous questions regarding reconstructing the initial and final state from the observed waveform.
Yes.
For electromagnetic case, you said the coefficients are known.
Yeah.
So it can be verified there.
Yeah, we are trying to check that, right?
Has
Basically,
it
the point
been
is
verified?
so complicated that you cannot do it analytically, right? We are trying to check numerically, right? Put some numbers and trying to see if basically it's a set of equations that involves initial momentum to the observed data, right? Initial and final momentum to the observed data. We are trying to see if it can be reversed by putting in explicit numbers.
So that has been verified actually?
No, we are in the process of doing it, right?
Okay.
But the formula is already too complicated
Sure.
that we have to do it numerically.
No, because one can take some special cases, because experimentally this can be tested, right?
That's true.
You can generate the waveform, measure it, and then reconstruct.
Yeah.
That can be directly verified.
Exactly, yeah. So my feeling is that if it works in the electromagnetic case,
Yeah.
it will most likely also work in the gravitational case. That the reconstruction should be possible in the gravitational case, because if it's not possible, it will only mean that somehow these functions are related, right? That we really have infinite number of data, right? Because you can have any n.
Yeah, yeah.
Right? And so if you cannot invert this, right, that will only mean that somehow there is some additional structure that even though there is infinite number of data, it only depends on a few combinations.
Yeah.
Right? So that is testable, and we are trying to test it.
Okay. Thanks.
Yeah. So I have a question.
Yes.
Here.
Okay. Yeah.
Here. I have a question. So this memory term, that a mu nu term,
yes,
that you have, can I think it as like energy absorbed by the metric itself, like locally in a space-time energy get absorbed?
Yeah. So this is not really energy absorbed by the metric, because a mu nu by itself, because it's a constant term, it doesn't carry any energy.
Okay.
Right? It's like, I mean, you can think of it as a locally it's like a gauge choice. It's like a gauge. Imagine for electromagnetic case, right? That some electromagnetic wave passes through. I mean, this happens in the electromagnetic case also, and A0 changes from a 0 value to some constant value, right? But constant A0 is doesn't carry any energy, right? Because the field strength is 0. The electric and magnetic fields are derivatives of the A0, right? Okay. So it doesn't carry any energy. Okay. This memory is similar to that.
Thanks.
So I'm not sure I'm understanding the negative U part correctly.
Yeah.
So, at the position of the detector for negative U, the gravitational wave or any effect due to the scattering should be 0, right? From causality point of view.
Okay, yeah.
But I'm not sure if when you mean negative U, what exactly do you mean?
So the point is that at negative U, what happens, you can say, okay, that the particles are coming in, right? Before they collide, how can they emit, right? The point is gravity has long range force, right? So when the particles are coming in, right, long before they actually collide, right, they are under each other gravitational force, right? And they start emitting gravitational radiation from far past,
okay,
right? And that's what we are seeing for negative U.
So that's not really then the effect of the scattering itself. Then.
Yeah. So negative U is not, okay, you can say that's also part of the scattering, right?
Okay.
But it's easier to understand because it's happening because of purely gravitational long range force.
Mm-hmm.
Positive U terms are more complicated.
Okay.
Right? Because positive U, you can see that it depends not only on the final data,
mm-hmm,
also on the initial data.
Mm-hmm.
Right? And that's a complicated effect of scattering as well as this effect of long range Coulomb force.
Yep, thank you.
See, these soft theorems are very general, right? So, one example that you said where in fact they are applicable is QED.
Yes.
Are there any other examples? So that lab verification is possible.
Lab verification, see in QCD people have tried to make some predictions, right, what kind of observables there may be, but QCD is so complicated that it's very hard to see whether you are seeing, what you are seeing is the effect of soft theorem or it's something else, right. So I think a clean prediction in the lab is only going to be in QED.
Only for QED?
Only for QED, yeah.
2D magnetic systems?
2D magnetic systems don't have a massless particle, right? Well, maybe, yeah, okay, if you have the collective modes, right, like magnons and photons, phonons, there may be soft theorems associated with those, right, which one may be able to verify, yeah, right. So, because soft theorem requires low energy excitations, right. So, magnons and phonons should have their associated soft theorem. All. Yeah, relativity also, but those we can look at phonon spectrum in the relativistic limit, right? I mean, there are examples where you can get such things. The relativistic limit, okay, these soft theorems in the form that I have given, right, those are relativistic, but there may be analogs of those even for non-relativistic ones, right? As long as there is low energy and low frequency, right? I mean, if you have non-relativistic dispersion relation, right?
Yeah.
Maybe you can still have. I'm not sure. Okay, this one has to check.
No, I'm saying that because long time effects, which are going to be almost zero frequency, but frequency will translate into wavelength only with some speed is given.
I agree. Yeah.
And if wavelength is not long wavelength, then you don't lose the information of the compact region where scattering is taking place.
That is true.
So in that sense, I mean, relativity is needed to get that relation.
But you can. You may be able to restate the soft theorem in a different way, right? Not in terms of time, okay, which as you said is related to relativistic ones, but just in terms of frequency, right? And those may also have effects in non-relativistic system. I am not completely sure. Right? This is something one has to study. I mean, it's basically the idea is that whenever you have some universal coupling, right? These soft theorems appear. The reason that there is soft graviton theorem and a soft photon theorem is because the coupling of the photon and graviton, low energy photons and gravitons to the rest of the system is universal. Right? Similarly, for phonons, right, because it's related to broken transits and invariants, right, there may be some universal couplings which may have some consequences. Right? Maybe not exactly in the form that I have described, but in some other form.
Okay, so let's thank the speaker one more time.
Thank you.
The effect of your brilliant lecture can easily be measured by the questions and the discussions that followed. So that's one measure of your effectiveness. So I want to just present a memento to our distinguished speaker. I just want to say something about this book before I give it to you. I'll take a couple of minutes. So this book was brought out in 2010. 2 years after my father passed away. It took 2 years to put this together. It's published by Springer, and we have 3 editors besides myself, John Clowder, a very distinguished mathematical physicist, and Professor C.R. Rao, perhaps one of the most eminent statisticians of the world. So there are papers in mathematics, physics, and in probability and statistics in this book. So besides tracing the early history of the Institute, which I have written about, and one of the most interesting things here is the collection of telegrams and letters that were received at the inauguration of math science from really well-renowned physicists and mathematicians like Niels Bohr, Abdul Salam, Murray Gell-Mann, Oppenheimer, and various people. So those telegrams are actually reproduced here. I just want to mention 2 papers in this volume. One of the privileges I had at the University of Florida was to have Professor John Thompson, the foremost group theorist, as my colleague. So in 2008, that was also the year my father passed away, Professor Thompson received the Abel Prize. And I happened to attend his lecture in Norway. And he spoke about his most recent work on the divisor matrix. This was the day after he received the prize winner gives a lecture. So then I came back from Norway, and 2 weeks later my father passed away, so I was thinking about putting a book together. So I went up to Professor Thompson and I said, I would like you to contribute an article to this book, because he knew my father from his visits to Florida and so on. So about a month later, Professor Thompson gives me this paper on the divisor matrix to be included in this volume. So I said, John, isn't this the talk you gave in Norway? I mean, isn't it supposed to be published with the Abel Foundation? And his response was, no, I think your father deserves it. So that paper is in this book. I just wanted to mention that. The second thing is, Sriram Abhyankar, about whom you have all heard about, very famous algebraic geometer hailing from Pune. He was my father were very close friends. So I wrote to Professor Abhyankar to also contribute a paper to this volume. And I didn't hear from him for about a month. And then he wrote back saying that he had just written a very long paper to be submitted to the Journal of Algebra, and that was to be in memory of his father, also a mathematician, last name also Abhyankar. And then he said, if you don't mind, I'll pull it out of the Journal of Algebra and I will give it for this book, but it will be dedicated to both fathers, my father and his father. So that paper of Abhyankar is also in this volume. So I'd like to present this volume to Professor Sen.
Thank you very much. Thank you. Thank you very much.
Okay, thank you so much for attending the lecture.